Every culture on Earth seems to remember the same nightmare. The Sumerians wrote about it on clay tablets. The Hebrews preserved it in Genesis. The Greeks told stories of Zeus drowning humanity. Hindu texts describe Manu and a great fish saving the world from total submersion. Aboriginal Australians, Native American tribes, Chinese chronicles, they all describe water rising up and swallowing everything. For centuries, people dismissed this as coincidence, or maybe just borrowed mythology spreading from one culture to another. A good story travels, right? But here's the thing that should keep you up at night. Geology says otherwise. Because when scientists actually started digging, literally digging into ice cores, ocean sediments and ancient riverbeds, they didn't find one flood. They found five separate, scientifically documented catastrophes spread across hundreds of thousands of years, each one massive enough to reshape coastlines, erase civilizations, and quite possibly plant the seed for a story that would be told and retold for thousands of generations. We're talking about a sea bursting through a narrow strait and drowning an entire basin in months. A chunk of the Norwegian seafloor collapsing and sending a wall of water toward ancient Britain. A frozen lake in North America breaking free over and over, carving canyons in days that should have taken millions of years. Ice sheets melting so fast the oceans rose faster than anything humans have seen since. And going back further than almost anything on this list, an entire dried-up sea refilling in what geologists believe was one of the most violent floods in this planet's history. 5 events, 5 continents, one recurring nightmare, written into rock, ice, and memory. So stick around, because by the end of this video, you'll understand why the flood myth isn't a myth at all. It's a memory. If you're using these to fall asleep, that's honestly why I make them. So subscribe, maybe, and tell me where you're listening from and what time it is right now. I check the comments constantly, and it's wild. Tokyo at sunrise, Chicago at midnight, all in the same thread. And if you want to actually support the channel, following on Spotify and leaving a 5-star review helps more than you'd think. Links in the description. Now let's go back to where the water first came for us. Number 1 on our list takes us to a stretch of water most people couldn't find on a map. The Black Sea, tucked between Eastern Europe and Western Asia, bordered by Turkey, Bulgaria, Romania, Ukraine, Russia, Georgia. Today it's just another sea, another blue patch surrounded by beaches and shipping lanes. But according to a hypothesis that shook the archaeological world in the late 1990s, this quiet body of water might be sitting on top of one of humanity's oldest nightmares. Here's the claim, and it's a big one. Somewhere around 7,600 years ago, give or take a few centuries depending on which researcher you ask, the Mediterranean Sea broke through a natural barrier at what's now the Bosporus Strait, that narrow ribbon of water running through modern Istanbul, and came pouring into a much smaller, much lower freshwater lake that used to occupy the Black Sea basin. Not a gentle trickle, not a slow seep over centuries. We're talking about a catastrophic sustained inflow, seawater crashing through a breach and flooding an entire basin with enough force and volume to expand the shoreline dramatically within the span of a single human lifetime, maybe even faster than that. 2 geologists from Columbia University, William Ryan and Walter Pittman, are the names most associated with bringing this idea into the mainstream. Back in 1997, they published research suggesting that as global sea levels rose after the last ice age, the rising Mediterranean eventually overtopped a natural sill, a raised ridge of land that had been holding it back from a separate, much shallower lake sitting in the Black Sea basin. Once that barrier gave way, the results were, by their estimation, apocalyptic in scale. Ryan and Pittman calculated that water could have poured through the breach at a rate roughly 200 times the flow of Niagara Falls. Try picturing that for a second. 200 Niagaras, all at once, funneling into a basin that wasn't prepared to receive it. And why does any of this matter? Why should a regional sea in Eastern Europe have anything to do with flood stories told by Sumerians in Mesopotamia, or Hebrews in the Levant, or any of the other cultures we mentioned a moment ago? Because of timing, and because of geography, and because of who was living there when it happened. See, around the time this flood is theorized to have occurred, the region surrounding the Black Sea basin wasn't empty wilderness. This was the era when Neolithic farming communities were spreading out of the Fertile Crescent, moving into Anatolia, into the Balkans, into the river valleys of Eastern Europe. These weren't hunter-gatherers wandering with the seasons. These were people who had committed to the land. They'd built permanent settlements. They'd domesticated crops and animals. They'd put down roots, literally and figuratively, in fertile lowlands near freshwater lakes and rivers, exactly the kind of terrain that a freshwater lake basin like the ancient Black Sea would have offered. Now imagine you're one of these early farmers. Your family has lived in this valley for generations. You know the rhythms of the water, the flooding season, the dry season, the places where the soil is richest. And then, over the course of months, maybe a couple of years, everything changes. The water doesn't recede like it always has. It keeps coming. It keeps rising. Places that used to be pasture become lake bed. Places that used to be dry ground become shoreline, and then become submerged entirely. If Ryan and Pittman's original estimates are anywhere close to accurate, the shoreline of the Black Sea basin could have expanded outward by tens of kilometers, swallowing hundreds, maybe thousands of square miles of what had been livable, farmable land. This is the part of the hypothesis that makes it so tantalizing and, honestly, so controversial. Because if an event like this really happened, to real people, living in a specific place, at a specific moment in prehistory, then you've got a plausible physical trigger for the kind of trauma that gets remembered. Not vaguely remembered either. The kind of trauma that gets passed down deliberately generation after generation, wrapped in story and metaphor and religious meaning. Because the alternative is that it simply gets forgotten, and something this devastating doesn't usually just get forgotten. Some researchers have gone so far as to suggest that displaced communities fleeing the rising Black Sea waters could have carried their experience with them as they migrated outward into the Danube Valley, into Mesopotamia, into the broader Near East, regions where, wouldn't you know it, some of the oldest recorded flood narratives on Earth eventually took shape. It's a compelling chain of dots to connect, a real geological event, a real displaced population, a real migration route, and stories that echo, at least in outline, what those people might have experienced. But before we get too far ahead of ourselves, and trust me, this is where things get complicated, we need to talk about what the rocks, the sediments, and the ancient shorelines actually show. Because not every geologist agrees with Ryan and Pittman's original numbers. Some think the flood was real, but far slower and less dramatic than originally proposed. Others question the timing entirely, and figuring out who's right means digging, quite literally, into the seafloor itself. So what do we actually see when we look beneath the waves? The first big clue comes from the shape of the seafloor itself. When oceanographers mapped the Black Sea basin with sonar, they didn't just see a simple bowl. They saw what looked like ancient shorelines, old terraces, stepping down toward the deep centre of the basin. Imagine a bathtub that used to be only half full for a really long time. The ring of soap scum around the middle is your old waterline. In the Black Sea, those soap scum rings are submerged beach ridges and wave-cut platforms sitting hundreds of feet below the modern surface. Ryan and Pittman pointed to one of those levels in particular, around 150 metres below present sea level, as the smoking gun. To them, that flat bench looked like the final shoreline of a much lower freshwater lake, stable for thousands of years, carved by waves lapping at a fixed level. Above that bench, no comparable terraces. Below it, deeper basin. Their argument went like this, that submerged shoreline marks the standstill before the flood. The Mediterranean rose, hit the Bosporus sill, broke through, and in a geological instant the lake jumped up toward modern sea level, drowning that old coastline in one catastrophic leap. But terraces are only part of the story. To really test the idea, scientists dropped cores into the mud at the bottom of the Black Sea. Long, cylindrical samples, each one a vertical time capsule, layer by layer, grain by grain. They record what kind of water filled the basin, what flowed in from rivers, what lived and died there. Near the bottom of those cores you find sediments laid down when the basin was clearly fresher. The chemistry is different. The microfossils are different. Shells from freshwater or brackish species, tiny organisms that don't tolerate full ocean salinity, dominate the record. That much pretty much everyone agrees on. Before the connection, the Black Sea was not just another arm of the Mediterranean. It was its own thing, lower and fresher. Then, higher up in the cores, there's an abrupt transition. Suddenly, the assemblage of microfossils shifts. You start seeing species that like saltier water, marine plankton that normally live in the Mediterranean. The isotopic signature, the ratio of oxygen isotopes locked into shells, points to increasing salinity and a new water source. To Ryan and Pittman, this sharp change looked like the sedimentary equivalent of a jump cut. One frame it's a lake, the next frame it's filling with seawater. They also noticed something about the sediments right around that transition. In some cores, the grains get coarser for a short interval, as if stronger currents swept through, bringing in heavier material that calmer conditions wouldn't move. To flood proponents, that's exactly what you'd expect from a powerful inflow blasting through the Bosporus, racing along the bottom and disturbing the mud as it went. But here's where the debate really heats up. Other teams went back, collected more cores, used more precise dating techniques, and didn't always see the same story. Some cores show that freshwater to marine transition is relatively gradual, smeared out over centuries rather than snapped in an instant. Instead of a sharp line in the mud, you get a blur. Salinity ramps up. Faunas mix. Freshwater species decline while marine species slowly become dominant. That kind of pattern can still fit a major inflow, but it doesn't scream single-year catastrophe in the same way. Then there's the question of timing. Ryan and Pittman originally placed the supposed deluge around 7,600 years ago, based on radiocarbon dates from shells at the transition layer and from drowned shorelines. Later studies redating those same materials with updated calibration curves nudged some of those ages older or younger. One influential group argued that Mediterranean water started spilling into the Black Sea much earlier, maybe as far back as 9,000 years ago, and that by 7,600 years ago the basin was already largely marine. If that's true, the classic dramatic picture, quiet lake for millennia, sudden breach, farmers watching their world vanish in a generation, gets harder to sustain. You might still have a flood, but stretched out over several human lifetimes. Enough to force people to move, but not necessarily enough to imprint as a single, unforgettable disaster. Some researchers also challenged the very idea that the Black Sea was dramatically lower than the Mediterranean in the first place. They point to alternative reconstructions of Ice Age sea levels and land elevations that make the height difference across the Bosporus sill much smaller. In those models, when the Mediterranean rose, the connection might have been re-established early and gently, more like opening a valve than blowing a dam. And then there's the direction of flow. Believe it or not, a few geologists have suggested that under certain conditions, water might actually have flowed out of the Black Sea toward the Mediterranean, at least for a while, rather than the other way around. That would imply a very different history for those submerged shorelines and terraces, one where the Black Sea wasn't a passive basin waiting to be filled, but an active part of a complex regional drainage system. So you end up with this tug of war, terraces that look like old shorelines, cores that record a salinity jump, but interpretations that range from Niagara on steroids to slow, messy, complicated transition. And all of this matters because the exact shape of that curve, sudden wall of water or creeping flood, changes what kind of story ancient people would have told about it. And speaking of people, those cores and shorelines don't exist in a vacuum. Around those ancient lake margins, on land that's now underwater, or sitting high above the modern coast, archaeologists have been finding clues of their own. To really understand whether this flood was a civilization-shaping catastrophe or just a bad few centuries by the water, we have to look at what was happening in the villages built along those vanishing shores. Imagine you're one of those villagers. It's the early Neolithic. You're not a wandering forager anymore. Your grandparents were, maybe, but your world is built around fields and herds and fixed houses. The old rhythm of follow the herds, follow the seasons has been replaced by protect the fields, store the grain, pray the weather doesn't betray you. And crucially, you live by the water. For early farmers around the Black Sea basin, shorelines were prime real estate. Rivers and coasts gave you fertile floodplains, easy transport routes, fish to supplement your crops, reeds for baskets and roofs, clays for pottery. The archaeological map of the region, from Bulgaria to northern Turkey to the Danube Delta, is dotted with Neolithic sites hugging lowlands and river mouths that would have opened onto that ancient lake. Here's where things get frustrating. The most vulnerable flood-exposed villages are precisely the ones least likely to survive in the archaeological record. If you build right next to a shoreline that later climbs dozens of meters, your house doesn't just rot in place, it gets eroded, buried, smashed, and in many cases completely submerged. When underwater archaeologists survey parts of the modern Black Sea shelf, they occasionally stumble on something unsettling. Traces of human activity that now sit in depths where no sane farmer would build today. Stone tools, worked timbers, cultural layers with charcoal and bone, lying on drowned river terraces and former coastal plains. They're patchy, contested, often hard to date precisely, but they hint that before the water rose, people were living on ground that's now under tens of meters of seawater. On land you see a complementary pattern. Some early Neolithic sites in the region look as if they were originally closer to a lake or sea margin than they are today. They sit on elevated benches and terraces that would have overlooked lower-lying plains. In a slow rise scenario, those benches become the new safe zones. People on the lowest flats get pushed upslope, crowding into what had once been marginal land. In a fast flood scenario, those benches are where the survivors end up after everything below is suddenly gone. When archaeologists look closely at the stratigraphy of certain sites, they sometimes see odd breaks in occupation. A village gets established, grows, leaves behind the usual debris of daily life. Hearths, pits, broken pottery, animal bones. And then abruptly there's a hiatus. No more artifacts. Then, centuries later, people are back, or a different community settles nearby with a slightly different toolkit, different house plans, different burial customs. Is that climate, disease, conflict, all of the above are possible? But along the Black Sea margins, some researchers have suggested that at least some of those gaps could reflect people being literally displaced by rising water. A flood removes the lowest village. Later groups resettle on higher ground, with new traditions shaped by the memory of having lost the old place. There are also hints in how Neolithic cultures spread. One of the big puzzles in Old World prehistory is the rapid appearance of farming communities stretching from Anatolia into southeastern Europe in just a few centuries. Pottery styles, house designs, domesticated plant and animal species, many of them look related, like branches of a family tree radiating out from a core zone in western Anatolia and the Aegean. Now drop that onto a map with a changing Black Sea shoreline. If the coastline was creeping or surging landward, the places where early farmers had first clustered around freshwater outlets and fertile deltas would have been among the first to vanish. That gives you a powerful push factor. You're not just exploring because you're curious, you're leaving because your fields are salting up. Your wells taste strange, and every year the water cuts a little closer to the graveyard. In that context, the fast spread of Neolithic ideas and people into the Balkans, up the Danube across the plains of what's now Romania and Ukraine, starts to look less like a leisurely migration and more like a series of controlled retreats. Groups carrying similar toolkits and farming packages leapfrogging inland, re-establishing their lifeways away from the encroaching shore. Some sites in the lower Danube and around the western Black Sea show exactly those kinds of cultural fingerprints, sudden arrivals of new pottery and building traditions that seem to come from the south or southeast, as if communities from around the ancient lake were stepping back, one river valley at a time. It's not conclusive, there's no burned sign saying "fled the flood," but the pattern is suggestive. And notice something else. In many Neolithic cemeteries from this broader region, you see careful treatment of the dead, grave goods placed with intention, sometimes even evidence of ancestor veneration. People were already thinking deeply about place, lineage, and the connection between land and memory. Lose the land, and you don't just lose fields, you lose the literal ground where your ancestors lie. If an advancing shoreline forced you to abandon the village where your grandparents were buried, where every stone and path had a story attached, that experience wouldn't just be logistical. It would be spiritual trauma, the kind of wound that begs for explanation, for narrative, for myth. So the archaeological picture we're left with is messy but intriguing. Drowned landscapes with scattered human traces offshore, onshore sites with gaps, shifts, and sudden cultural arrivals, a farming population whose preferred habitats were exactly the ones most at risk from a rising Lake Tennessee. Put yourself back in that position. You're part of a world where the dead matter, the land matters, and the stability of the seasons feels like a covenant. And then, over the span of your parents' lives, or maybe your own, that covenant starts to break. The water moves, the coast redraws itself, villages vanish. What kinds of stories would you start telling to make sense of that? Maybe at first the stories are small. Your grandfather remembers when the inlet was just a marsh where you trapped fish by hand. Your father remembers when the marsh turned brackish and your cousin got sick from drinking the water. You remember when an autumn storm, bigger than any in living memory, drove waves right over the old path and never quite went away. Each generation adds a layer. By the time your grandchildren are listening, the marsh is gone, the path is gone, the old village is a rumour beneath the waves. But what survives isn't the bathymetry, it's the emotional geometry. Once, the elders say, the sea was far away. Then it grew angry. It rose up and took the land. Notice how that works. Even if the actual process was a weird mix of slow creep and sudden pulses, freshwater outflow reversing, salinity levels changing, shorelines stepping inland in fits and starts, human memory doesn't track gradients very well. It tracks thresholds, the year the shoreline first eats the graveyard, the night the protective dune breaches, the storm that knocks down the last standing shrine by the old harbour. In reality, it's decades of erosion. In memory, it's the time the waters broke their bounds. Now imagine you're not the only community telling that kind of story. All around the ancient Black Sea basin, different groups would have been watching versions of the same drama. Some on the low western plains, some along the southern deltas, some in river valleys that suddenly started backing up with higher base levels and flooded bottoms. Each group pins the turning point to their own experience, their own sacred places, their own losses. But when they move, and we know they did move, those stories start to travel. A displaced group from one drowned coastal plain joins, trades with or marries into another group farther inland. Around the fire they compare notes. In our homeland, the waters came up and swallowed our fields. Us too. In our grandparents' day, the river ran clear. Then one year it turned bitter and the fish died. We have a tale like that as well. Pretty soon the specific geography starts to blur. What remains is the pattern. Land, people, covenant, broken by water. This is where the Black Sea scenario becomes interesting in the context of global flood myths. It doesn't need to have been a planet-wide cataclysm to seed stories that feel world-destroying to the people who told them. Because for a Neolithic farming village, the world isn't Earth as a globe. It's the basin you can walk around, the horizon you know, the network of rivers and trails that link your people and your gods. If that entire known world, your coasts, your deltas, the places your trade partners live, starts shifting at once, it absolutely qualifies as everything in narrative terms. Think about what happens when those farming cultures keep expanding. Over centuries, descendants of Black Sea-adjacent communities move up the Danube over the Balkans into the plains of Central Europe, into Anatolia's interior. Others, influenced by similar shoreline changes in the Aegean and Eastern Mediterranean, spread through the Levant and Mesopotamia. Each migrating strand carries fragments of its own deep-time disaster lore. Some strands will have very specific "once there was a great lake that became a sea" motifs. Others will only retain the emotional core: disobedience, forgetfulness, or hubris followed by punishing water. As these groups interact with even more distant cultures, those motifs get remixed. A Mesopotamian city-state that already lives with seasonal flooding on the Tigris or Euphrates might graft an older inherited memory of lost coastal lands onto its own experience with river catastrophes. Over generations, you get a story where a god sends a flood not just over a valley, but over all the land. The storyteller is not lying. To him, all the land is the entire social universe he can imagine. Something similar might happen on the northern side. Steppe groups with origins near flooded Black Sea margins push out onto the Eurasian grasslands. Their cosmologies evolve in open country environments, but they still tell of a time before the waters reached the high hills, when there was more land, more game, more room. Mixed with later ice melt events and local river floods, those tales drift, harden, and eventually show up as mythic floods in cultures far removed from the original shoreline. This also helps explain why certain themes recur across flood narratives that are otherwise unconnected. The righteous survivor who listens to a warning, the boat or high refuge, the animals carried or saved. The idea that after the waters recede, the world has been reset, contracts have been rewritten, and humans must behave differently. All of those make sense if you're remembering not just a physical disaster, but a cultural bottleneck, whole communities squeezed into smaller territories, forced to renegotiate how they live, who they marry, what they owe each other and the gods. From the standpoint of geology, the Black Sea event, if it happened as dramatically as some models suggest, is a regional sea level adjustment tied into broader post-Ice Age changes. From the standpoint of human storytelling, it's apocalypse. And apocalypse stories don't stay put. They spread with people, they get translated into new symbolic languages, they fuse with other floods, glacial outbursts, river avulsions, coastal storms until what began as the sea came in through the strait and swallowed our shores becomes, in a later culture hundreds of miles away, once the entire Earth was covered and only a handful survived. That's the kind of echo this hypothesis is trying to catch. Not a one-to-one match with any single legend, but a plausible seed event big enough and traumatic enough that its shock waves could still be rippling through human myth thousands of years later. But of course, not everyone is convinced that's what the rocks and the stories are really telling us. Some geologists look at this whole picture, the rising shorelines, the changing salinity, the drowned valleys, and shrug a little. Not because nothing happened. Everybody agrees the Black Sea changed dramatically as the last ice age ended. The argument is about tempo, magnitude, and framing. Did the Mediterranean really crash through the Bosporus like a broken dam, sending a roaring wall of water sweeping hundreds of kilometres inland in a matter of months? Or was it more like a series of escalating pay raises, still life-changing but spaced out over decades, even centuries? One major criticism goes straight to the heart of the sudden part. When oceanographers and geophysicists model the hydraulics of the Bosporus, some of them get numbers that look underwhelming compared to the original headlines. Yes, a big head difference between the Mediterranean and the Black Sea would drive strong inflow, but the channel is narrow, shallow in places, and friction is a real thing. Under many plausible configurations, you don't get a Hollywood megaflood. You get a powerful, sustained current raising the lake tens of meters, but stretched out over hundreds of years. For a farmer living 30 meters above the old shoreline, that difference matters. In the dramatic version, your fields disappear in your own lifetime. In the slower one, your grandparents talk about the old beach. Your parents move the fields. You're born already inland. The story feels less like sudden wrath and more like the world's slow, grim shrug. Then there's the timing problem. Radiocarbon dates from shells, drowned soils and coastal sediments don't all line up neatly around a single year zero. Some point to a relatively quick jump somewhere around 7,500 to 7,600 years ago. Others smear the rise across a broader window from about 9,000 to 7,000 years ago. Still, others suggest the Black Sea may already have been brackish, not purely fresh water, before any big spillover. If that's true, then the event doesn't look like a pristine lake being annihilated by an invading sea. It looks more like a lake that's already flirting with the ocean, finally committing to the relationship. Critics also point to alternative reconstructions of global sea level. A lot of the early drama came from tying the Black Sea story to specific meltwater pulses, brief intervals when world oceans seem to jump faster than usual as ice sheets collapse. But not everyone agrees on exactly when those pulses hit, how big they were, or whether enough extra water was available at exactly the right time to produce the kind of overfill needed for a catastrophic Bosporus breach. Shift those global curves by a few hundred years, and the neat alignment between Mediterranean rises and Black Sea drowns gets fuzzier. On the archaeological side, the picture is equally muddy. If a sudden basin-wide flood erased Neolithic coastlines, you might expect sharp breaks in settlement patterns, clear signs of mass abandonment, or a distinct post-flood cultural horizon ringing the new shores. What we actually see is more ambiguous. Communities relocating, yes, but also evidence of continuity, reuse, adaptation. People don't just vanish, they pivot. Some researchers argue that looks more like long-term encroachment than a single disaster year. And then there's a more philosophical objection. Linking a specific geological event to a broad family of myths is tempting, but it risks cherry-picking. For every flood legend you can plausibly connect to rising Black Sea waters, there are others clearly rooted in river systems, monsoon failures, tsunamis, or glacial lakes on the other side of the world. Why privilege one basin as the real flood behind so many stories when multiple, independent world endings were available across the Holocene? To some, the Black Sea hypothesis started to look less like a careful inference and more like a just-so story. Find a dramatic geological curve, draw an arrow to a famous myth, call it solved. But here's where the debate gets interesting, rather than just dismissive. Even the skeptics agree on a few key points. Shorelines moved, salinity changed, human communities were displaced, sometimes repeatedly. The Black Sea was not a static bowl with a single bad day. It was a dynamic system riding the aftershocks of deglaciation. So the real questions now aren't simply catastrophic or not, but how fast in different places, how often, and who was living there to experience which phase. New tools are starting to sharpen those questions. High-resolution cores from the sea floor can pick up subtle layers, storm beds, turbidites, sudden changes in microfossils that record short, intense events superimposed on long, slow trends. Submerged river channels, imaged with sonar, can tell you how quickly valleys drowned. Ancient DNA from sediments might one day track when marine species invaded what had been a freshwater ecosystem, giving another clock for salinity change. On land, more precise radiocarbon calibration and better excavation of early farming sites around the basin are starting to map who was where, when. Did certain cultural traditions vanish right as the waterline crossed their zone? Or did they survive inland, carrying very specific memories of lost coasts? And in myth studies, researchers are getting more cautious and more sophisticated. Instead of hunting for a one-to-one correspondence, this story equals that flood. They're looking at how different kinds of water disasters tend to leave different narrative fingerprints. Does a tale emphasize days of rain, or a single breaking barrier? A rising sea or a surging river? Slow encroachment or instant annihilation? Placed in that broader comparative framework, the Black Sea no longer has to be the singular origin of any one tradition. It becomes one node in a global web of Holocene water shocks, each feeding into the evolving human sense that the boundary between land and sea, order and chaos, is negotiable, but only up to a point. So where does that leave the grand idea that the Bosporus breach explains the Great Flood? Most researchers today would say it might be one of the ancestors. Not the only one, not the pure original, but an important chapter in a much longer, messier family history of floods. A real rising of waters in a real place, reshaping real lives. And as we move on, we'll see it's just the first of several layers science has uncovered, each one a different kind of deluge, each one perfectly capable in its own time and place of convincing people that their entire world had just gone under. Number 2 on our list takes us far from calm rising seas and slow drowning coasts into something much more violent. If the Black Sea story is about the shoreline creeping up year after year, the next one is about the ocean itself, standing up, taking a swing at the land, and then dropping back down as if nothing happened. Geologists call it the Storegga slide, roughly 8,200 years ago, off the coast of what is now Norway. A piece of the seafloor lost its grip and moved. Not a little slump, not a minor submarine landslide, like the ones that happen on continental margins all the time. We're talking about one of the largest known underwater landslides in Earth's recent history. Picture the continental shelf off Norway as a giant, gently sloping balcony hanging out over deep water. Over tens of thousands of years, ice sheets grind rock into powder, rivers deliver mud, ocean currents rearrange it. All that sediment piles up on the edge of the shelf like someone stacking one too many boxes on the lip of a table. Eventually, the stack becomes unstable. When researchers mapped the seafloor in the Norwegian Sea, what they saw wasn't subtle. The Storegga region is carved by an enormous scar, a bite taken out of the continental margin. Behind it, chaotic terrain where intact layers used to be. In front of it, a tongue of debris extending hundreds of kilometres downslope into deeper water. Volume estimates are staggering. Somewhere on the order of 3,000 cubic kilometres of sediment moved. That's hard to wrap your head around. So translate it this way. More material than all the rivers on Earth currently carry to the ocean in an entire year, multiplied many times over, let loose in a single catastrophic event. And all of that mass didn't just quietly rearrange itself in the dark. When you yank that much sediment off a continental shelf in one go, you displace water. A lot of water. That displacement launches waves, and those waves don't care about your Mesolithic fishing camp, your beach, or the low-lying plains you thought would be dry forever. But hold that image of the waves for a minute, because before we talk about the tsunami, we need to talk about timing and cause. How do we know when this happened? Like the Black Sea story, the Storegga event is dated from multiple lines of evidence that all converge on the early Holocene. Cores drilled into the slide debris itself capture broken, mixed-up layers sitting on top of otherwise orderly marine sediments. You can date tiny fossils, shells of plankton, foraminifera, within those layers using radiocarbon methods. On land in places like coastal Norway and eastern Scotland, geologists find odd, clean layers of marine sand, sandwiched between peat and soil that formed above sea level. Those sand sheets often contain shells and organic material that can also be radiocarbon dated. The ages line up roughly 8,100 to 8,300 years before present, clustering around that 8,200-year mark. This is not guesswork from a single sample, it's dozens of cores, multiple coastlines, independent labs. There's some spread in the numbers, as always, but the consensus is tight enough that most researchers are comfortable calling it one big event somewhere around 8,200 years ago. That timing is interesting for another reason. Around the same time, climate records from Greenland ice cores and lake sediments across the northern hemisphere show a brief cold snap, the so-called 8.2 kiloyear event. It's thought to be triggered by a sudden pulse of freshwater from collapsing North American ice-dammed lakes, which temporarily disrupted ocean circulation. Some have wondered, could that climate blip and the Storegga slide be connected? The mainstream view is that they're mostly separate stories that just happen to overlap in time. The freshwater pulse seems to come from the other side of the Atlantic, and its signature shows up a bit earlier than some of the best Storegga dates. But in a world still adjusting to the final decay of ice sheets, it's not crazy to imagine multiple systems teetering on the edge at once. Oceans, ice margins, and, as it turns out, submarine slopes loaded with unstable sediment. So what actually triggered the slide? Here, the debate opens up. One camp points to simple oversteepening in gravity. Over thousands of years, glaciers and rivers feed enormous amounts of loose material to the shelf edge. Gas, hydrates, ice-like compounds of water and methane, frozen in the sediment, may help hold things together, but they're sensitive to pressure and temperature. As sea level rose after the last glacial maximum and bottom waters warmed, those hydrates could have destabilized. Remove just a bit of that internal glue, and a critical part of the slope fails, pulling the rest along in a gigantic chain reaction. Others highlight earthquakes. The North Atlantic region is not as quake-prone as, say, Japan, but it's not seismically dead either, especially during and after glacial periods, when unloading of ice sheets can adjust crustal stresses. A moderate to strong earthquake hitting an already oversteepened, gas-rich sediment pile could be the proverbial last straw. There are also ideas about slow creeping deformation, small slips, minor slides, subtle changes in pore pressure gradually weakening the margin until one day it crosses a threshold. At that moment, the failure front races along the shelf, and what had been millimetres a year becomes metres a second. The frustrating thing about submarine landslides is that the ocean erases their forensic trail. On land, you can map fault breaks, liquefaction structures, toppled trees. A kilometre underwater, much of that fine detail gets scrambled. So instead of a neat, it was definitely an X-magnitude earthquake at this time on this fault. What we have is a convergence of risk factors. Huge volumes of unconsolidated sediment, a steepened continental slope, possible gas hydrate breakdown, a post-glacial world still shivering through its last structural adjustments. In that setting, an event like Storegga stops looking like a bizarre fluke and starts looking like an especially big roll on a loaded dice. What's not in doubt is the consequence. When that margin went, the sea surface above it did not stay flat. It lifted, shifted, and sent energy racing outward across the North Atlantic in a series of waves that would, for a few terrifying hours, redraw the map of Northern Europe. And the evidence for those waves is written not only on the seafloor, but high above today's tide lines, in places that should never have seen the ocean unless something extraordinary happened. Start with Scotland. You're walking across what looks like perfectly ordinary lowland, patches of peat, old dune fields, river mouths that open onto modern beaches. The ground feels solid enough, but when geologists sink cores into those quiet landscapes, they keep pulling up the same strange signature. Peat, then a sharp contact, then a clean, well-sorted layer of sand and marine shells, then peat again. It's like someone briefly turned that field into a shallow bay, dumped a blanket of seafloor material across it, and then walked away. Those sand sheets aren't enormous in thickness, often just a few tens of centimetres, but they're weird in context. They sit above what would have been mean sea level at the time. They contain marine microfossils that live offshore, not in salt marshes. Sometimes there are ripped-up chunks of peat and soil mixed into the lower part of the sand, like the wave chewed up the land as it came in. And they're continuous. Follow them laterally, and you can trace the same distinctive sand bed stretching hundreds of metres, even kilometres, inland from the ancient coastline in places like the Moray Firth and the east coast of Scotland. In some valleys the deposit pinches out only where the land rises high enough that even an extreme wave wouldn't have reached. Now here's the key twist. When you radiocarbon date the organic matter just below and just above these sand layers, bits of plant material in the peat, maybe a piece of wood, maybe shells that settled afterward, you land right back in that 8,200-year window. Different sites, same basic age. The pattern is so consistent that researchers began calling it the Storegga Tsunami layer, long before the whole story was fleshed out. Cross the North Sea in your mind to Norway, closer to the source. Along the fjords and low coastal plains of western and central Norway, something very similar shows up. Again, you've got terrestrial sediments and bogs that formed on what was then dry land. Again, the normal sequence is abruptly interrupted by sandy, shell-rich horizons that have no business being there unless the sea came far inland in a single violent episode. Some of those Norwegian tsunami beds are spectacular. You see grading from coarse material at the base, pebbles, shells, ripped-up clasts of older sediment, up to finer sands at the top. That's classic high-energy run-up behaviour. Fast, erosive flow on the way in, then slower, settling water as it retreats. In a few places you even get multiple sand pulses stacked on top of each other, hinting at more than one major wave hitting in succession. Again, the dates from these inland marine layers line up with the timing of the slide, and their elevation tells a second part of the story. After you correct for post-glacial uplift, the way Scandinavia has been slowly rebounding upward after losing its ice load, Some of these tsunami beds sit several meters above what the local high tide would have been 8,000 years ago. That's not storm surge. That's not a slightly bad day at the beach. That's water being physically forced onto land by a massive displacement event. But the trail doesn't stop on the rocky margins of Scandinavia and Scotland. It extends into what used to be, quite literally, another country. In the early Holocene, the floor of today's North Sea wasn't fully submerged. Vast areas of that shallow basin were dry land, a low, rolling plain, sometimes called Doggerland, crisscrossed by rivers and wetlands, home to deer, aurochs, and Mesolithic hunting camps. As sea level rose, Doggerland shrank, but around 8,200 years ago, large tracts were still above water. We can't walk out there now and dig into its soils, but we can core the margins. Along the coasts of eastern England, the Netherlands, Denmark, and the German Bight, basically the modern shorelines that rim the former Doggerland plain, geologists have found inland marine sand sheets that look suspiciously like the Scottish and Norwegian ones. Once again, peat and freshwater sediments below, then a sharp, erosive base, then a layer of marine sand rich in offshore microfossils, then a return to non-marine deposition on top. In some Dutch and Danish sites, the tsunami sands overlie what had been tidal flats or coastal marsh, suggesting the wave came in over an already encroaching sea, then kept going, flooding areas that would normally have been safe behind dunes or higher ground. A few cores from buried channels in the southern North Sea show coarse marine sediments draped over what had been river and floodplain deposits. The geometry is exactly what you'd expect if a large wave poured across the low-lying landscape from the northwest, filled valleys and depressions, and then drained back toward the open basin. When these marginal tsunami deposits are dated, they again cluster around that same early Holocene window. They're slightly younger or older here and there, that's normal for radiocarbon work, but the overlap is strong enough that most researchers see them as part of the same trans-North Sea event. Put all of this together and a coherent picture emerges. A slide off Norway sends waves in all directions. Near the source along the Norwegian margin, the run-up is high and brutally energetic. Across the basin, Scotland gets hammered. Around the edges of Doggerland, water surges over low coasts and river mouths that had, until that day, been reliably dry. And remember, this is just what we can still see, 8,000 years later, in the few places where the right kinds of sediments were preserved and later exposed or cored. The real experience for the people living on those coasts and plains is something we'll get to next. So imagine you're one of those people. It's the early Holocene, Mesolithic Europe. There are no fields of grain, no stone farmhouses, no harbours. Just coasts and rivers and wetlands and light, mobile camps. Your world is made of wood, hide, bone and memory. Along what's now eastern Scotland, northern England, the Danish and Dutch coasts, small bands of hunter-gatherers have spent generations learning the moods of the sea. They know the tides without clocks. They can read the sky, the smell of the air, the way waves break on a sandbar, and predict whether it's safe to haul out in a logboat. They've watched the shoreline creep inland across grandparents' lifetimes. Sea level is rising as the last big ice sheets melt. Old campsites on what used to be dry ground are now salt marsh or open water. But that rise is slow. It's a background creep, something you talk about in stories that begin with, "When I was a child, that headland was twice as far out." On the day of the tsunami, that background change stops feeling slow. Along those Mesolithic coasts, most people probably weren't camped directly on the beach. If you live by the sea long enough, you learn to give it a little space. Camps sit on low terraces, behind dunes, along estuaries where fresh and salt water meet, and the fishing is good. People are used to storms. They've seen big waves, flooded flats, high winds tearing at shelters. What they hadn't seen was the sea arrive all at once. A tsunami doesn't look like a normal breaking wave when it hits shallow water. Often it's more like a fast-rising tide, a wall of churning, debris-filled water that keeps coming. One moment the tide is out and you can walk on the mudflats. Minutes later, those same flats are under several meters of moving water, jammed with logs, carcasses, stones, and anything else the wave picked up on its way in. For Mesolithic groups on low coastal plains and around Doggerland's rivers, that would have been the difference between inconvenience and annihilation. A normal storm flood you can ride out on slightly higher ground. A Storegga-class tsunami doesn't care about your favourite sand ridge. Some camps would have been in exactly the wrong place. Narrow estuaries, low saddles between dune ridges, coastal inlets that acted like funnels. In those spots the wave has nowhere to go but up and in. Archaeologists working on the British and continental coasts sometimes find Mesolithic sites that simply stop, a scatter of tools and hearths in one layer. Then, above it, marine sand and shell, and then nothing from that community afterward at that location. That absence is part of the story. Doggerland itself makes it even starker. Before full submergence, it seems to have been a kind of Mesolithic heartland. Where later maps show open water, there was once a vast low plain connecting Britain to the continent. Rivers drained into broad estuaries. There were lakes, marshes, upland pockets. People moved across it seasonally, hunting red deer and aurochs, fishing, trapping waterfowl. We know this from dredged bones and artefacts hauled up by trawlers, from seismic surveys that reveal buried river systems, from bits of worked flint and antler tools that don't belong on the modern seafloor. Now add the tsunami. If you model wave propagation from the Storegga slide, some reconstructions show crests sweeping right across the still shallow North Sea and crashing into the remaining dry parts of Doggerland. Numerical studies suggest run-up heights of several meters above the then sea level in the lowest areas. Not necessarily enough to erase the entire landscape in one go, but more than enough to turn river valleys and basins into lethal traps. Picture being camped on a low ridge in the middle of that plain. The nearest coast might be dozens of kilometers away in every direction. You don't think you live by the sea. The horizon is land and sky. And then, without warning, the river in the valley below reverses, swells, and becomes a moving wall. Water roars in from what feels like all sides, because on a very flat surface, it effectively does. If you survive that day, maybe because your group happened to be inland or on slightly higher terrain, you don't just lose people. You lose places, fishing spots, foraging grounds, burial sites, paths between seasonal camps. Sections of the plain that were marginal already because of slow sea level rise may be permanently transformed. Channels deepened, dunes flattened, peat swamps ripped open and replaced by brackish lagoons. And this is where the big debate kicks in. Did that single catastrophic event kill Doggerland as a human homeland? Or was it just one very bad day in a much longer drowning? On one side, you've got a compelling narrative. Doggerland is already shrinking as the seas rise. Then the Storegga tsunami hits, blasting salt water across low plains, destroying camps, maybe wiping out entire communities and cutting land bridges sooner than they would have failed naturally. In this view, people don't just adapt gradually, they experience a shock. Afterward, whatever's left of the plain is more broken, more dangerous, less attractive. Groups pull back toward the emerging island of Britain and the continental coasts. A great flood moment becomes the tipping point between a connected world and a fragmented one. On the other side, many researchers argue for a slower fade out. Sea level continues to climb for centuries after the tsunami. Even without a giant wave, Doggerland is destined to go under. The archaeological record shows Mesolithic communities persisting along the shifting coasts, adjusting to new shorelines, exploiting estuaries as they form. The tsunami in this telling is a dramatic episode, but not a permanent, region-scale game-changer. It's like a terrible storm that wrecks certain areas but doesn't rewrite the long-term map on its own. The sediments don't give us an easy answer. We see the sand sheets. We see pre- and post-tsunami environments, but we don't have a continuous, neatly layered sequence of Mesolithic camp after Mesolithic camp, transitioning from dry upland to tidal marsh to open sea, all nicely dated. Much of Doggerland's story is literally underwater, sliced up by trawler nets and preserved only in scraps along the margins. What we can say is that right around that 8,200-year mark, Europe's coasts are under pressure from two directions at once: a long, relentless rise of the average sea line, and, superimposed on that, at least one day when the ocean behaves in a way nobody in living memory had seen before. And when you put humans into that kind of double squeeze, slow background change, plus sudden catastrophe, you don't just reshape landscapes. You reshape stories. We'll come back to those stories. Before we do, we need to talk about how an event like this actually survives in memory for thousands of years, and what the Storegga tsunami might have sounded like by the time it was retold as myth. Let's start small. You're a child growing up on one of those post-tsunami coasts. You don't remember the wave itself. You weren't born yet. But the adults do. Maybe your grandmother has a scar on her leg from where debris slammed into her as she ran. Maybe your uncle lost his brother that day. Maybe half your clan's old fishing grounds are now a tidal channel nobody dares cross. The landscape itself has become a story prompt. Humans don't process that through geology. We process it through narrative. So when the wind howls and the tide comes in high, someone tells you, once the sea came all at once. It climbed higher than that dune. It took the boats and the dogs and the firewood. It swallowed the low forest. Don't camp too close to the water. The sea remembers. That's the seed. At first, it's basically an eyewitness account with some emphasis added. But memories degrade fast. The raw, sensory details don't survive intact for more than a generation or two. What lingers is the emotional outline. We were safe. Then we weren't. The sea crossed a line it usually keeps. Some people didn't come back. To keep that outline from fraying, you wrap it in pattern. You say the wave came as punishment for breaking a taboo. Or it was sent by a sea being, angry that people took too many fish or buried their dead in the wrong place or failed to perform a ritual. You turn a one-off geological freak event into something morally and cosmologically meaningful. Because if it's just random, there's nothing to learn from it. Anthropologists studying modern coastal societies see this over and over. Rare, shocking events don't become enduring stories unless they hook into rules. Don't build here. Don't go out when the water does that. Always leave an offering at this rock. The myth survives because it's not just a story about the past, it's a guideline for the future. And the rarer the event, the more myth-like it has to become to survive. Storm surges happen often. Everyone's seen those. They don't need a grand narrative. They're part of living memory in every generation. But something like a Storegga-class tsunami, that might be a truly once-in-many-lifetimes shock for a given coastline. Unless you institutionalize it as story, it dies with the last survivor who saw it. This is where oral tradition does something remarkable. It doesn't preserve exact transcripts, it preserves structures. You can change the names of the spirits, shift the setting from one headland to another, Update the technology in the story as people adopt boats or nets or pottery, and the core warning can still survive. The water reached higher than you think it can. It came from far away. It took everything on the low ground. Only those on the heights lived. You can hear that same skeleton in a surprising number of flood myths. In some Pacific Island traditions, there are stories about waves so big they climb the mountains, leaving survivors only on the highest ridges. In parts of Japan, tsunami stones mark maximum run-up heights from historical quakes, often inscribed with warnings not to build below that line. Those stones are literal geology, but they function the same way as myth, carrying the memory of a rare disaster forward. In Northern Europe, we don't have direct myths from 8,000 years ago, obviously. But later, Norse and Germanic traditions are full of motifs where the sea or a flood temporarily erases the boundary between worlds. Lands sink, islands appear and vanish. Gods fight sea monsters that threaten to drown the earth. You don't have to believe any one of those is about Storegga to see the pattern, a culture that understands at some deep level that the ocean can redraw the map. And then there's the way these stories travel. Mesolithic people weren't static. Bands met at seasonal gathering spots, exchanged goods, exchanged marriage partners, exchanged gossip. In that gossip are stories. Far to the north, the sea came over the land. Across the shallows, people say the ground shook and the water rose, even if the Storegga wave itself only devastated certain shorelines. The account of it could spread far along the web of rivers and coasts. The farther it travels, the less tied it becomes to a specific river bend or bay. A Scottish group might say it happened to their grandparents. A group on the Dutch coast, hearing it third or fourth hand, might translate it into their own landscape. The wave came here, it nearly reached that hill. Over centuries, the story unmoors from its original coordinates and becomes an archetype. The great flood that once reset everything. That's the strange power of these rare coastal catastrophes. They are local in physics but global in imagination. A single underwater landslide off Norway sends a wave into a handful of vulnerable lowlands. But the human reaction to that wave, the grief, fear, awe, and need to explain, creates a template for when the sea breaks the rules that can be reused whenever coastlines change, wherever people live at the edge of land and water. And once you have that template, you can attach it not just to tsunamis, but to anything that feels like the world drowning. Long-term sea level rise, estuaries turning to bays, storms that carve out whole chunks of shore. Which raises a bigger question. When we hear later flood myths from very different cultures, are we hearing one specific ancient disaster echoing down the millennia, or the accumulated memory of many Storegga moments stitched together into a single overpowering narrative? To answer that, we need to step back from this one landslide and look at what happens when coastlines everywhere start drowning at once. Here's where we have to pump the brakes a little. So far, this has all sounded very cinematic. Giant underwater collapse, killer wave, drowning land bridge, birth of flood myths. It's a compelling story, but the rocks don't actually give us a high-def recording of what happened. They give us a few grainy frames and a lot of blank space in between. Start with the thing everyone wants to know. How big was the wave, really? If you read popular pieces, you'll see numbers thrown around. 10 metres high, 20 metres, more than 100 feet. Impressive, terrifying, very clickable. But those numbers come from models, not measurements. And models are only as good as their inputs. We don't know exactly how fast the Storegga slide failed, how many separate pulses there were, how much material moved at once, or the exact shape of the seafloor 8,200 years ago. Change those parameters and your simulated tsunami can go from wall of water obliterates everything to still serious, but mostly a brutal storm surge on steroids. The deposits on land don't fix this for us. Yes, you can say, at this spot, at this time, the sea definitely came farther inland than usual and left marine sand on top of peaty soil. That's solid. But translating that layer thickness and grain size into an exact wave height is messy. Run-up depends on local topography, vegetation, how wet the ground was, what the shoreline looked like right then. Two coasts can see very different flooding from the same offshore wave. There's also the muddy problem of reach. We've found Storegga-aged tsunami layers in parts of Scotland, along some Norwegian coasts, in a few North Sea locations. That does suggest a regional event, but absence of evidence is not evidence of absence. A coastline might have been hit and simply not preserved the layer, or the layer might be buried too deep or eroded away, or we just haven't looked in the right spot yet. So when you see a neat map tracing a sharp line, the wave reached up to here, that's not a boundary drawn by the tsunami. That's a boundary drawn by where we've currently managed to find and date the sand. And then there's the most awkward question of all. What can't these layers tell us? They can't tell us how many people died. A thick sand sheet doesn't equal a high body count. People might have seen the water draw down and bolted for higher ground. Or they might have been inland that season, or a bad storm the previous winter might actually have killed more people than the tsunami did. The layers also can't tell us what people believed about it. Geology can say, this valley flooded abruptly. It can't say, and then they invented a sea god to explain it. You can speculate about myth connections, you can look at later stories and wonder, but you can't draw a straight arrow from one patch of sand to a specific saga written thousands of years later. They can't prove Doggerland was wiped out in a day either. The timing of Storegga and the long, slow Holocene sea level rise overlaps. That makes it tempting to imagine the wave as the final death blow to the North Sea land bridge. But the bathymetry suggests much of Doggerland was already low, marshy and fragmenting into islands. The tsunami may have been a brutal punctuation mark, but the sentence of drowning was already being written, one storm and spring tide at a time. On top of that, other processes can mimic parts of the signal. Storm surges can push marine sand inland. River floods can rearrange sediments in confusing ways. Later erosion can scramble the sequence and make a gradual process look more sudden than it was. Even with careful dating, you're always fighting the fact that the Earth is an active editor, constantly revising its own archive. So what are we left with if we strip away the wishful thinking? We have very strong evidence that a massive submarine landslide off Norway happened around 8,200 years ago. That it generated a tsunami large enough to overtop normal coastal limits in multiple parts of the North Atlantic margin. That people were living there when it hit. That some of those people probably watched the sea climb into places it had never reached in their parents' or grandparents' lifetimes. Beyond that, the story gets fuzzier. We can sketch scenarios, but we shouldn't confuse those scenarios with certainty. And that's actually the bigger lesson of this whole many floods idea. Each geological layer gives us proof that the world has, again and again, staged its own little apocalypses, regional, violent, unforgettable to the people who survived them. But none of those layers comes with a built-in label saying, "This is the great flood from your favourite myth." Instead, we see a pattern. Coasts change, seas invade, landscapes drown. Humans watch, suffer, move, and explain. Over thousands of years, those explanations pile up and blend together. Storegga is one layer in that stack. To see the full shape of the story those layers tell, about how once there was a flood, becomes a human default narrative. We have to zoom out beyond this one submarine landslide and look at other places and other times when the water didn't just send a wave, but tried to rewrite entire continents. 3. Missoula Megafloods, Channeled Scablands, Pacific Northwest. If Storegga was a regional shockwave that slapped coasts and then retreated, our next flood is something different. This one didn't just surge over the land, it tried to grind the land itself into a new shape. To find it, we leave the drowned plains of Doggerland and move to what's now the northwestern United States, eastern Washington, parts of Idaho and Montana, and down the Columbia River toward the Pacific. Today, if you drive across that landscape, it can feel strangely empty. Big skies, rolling wheat fields, a few rivers cutting through dry plateaus. But hidden in plain sight is one of the wildest crime scenes in Earth's recent history. A place so aggressively reshaped by water that the only sane conclusion should have been a flood did this. Except when one geologist actually said that. Almost no one believed him. His name was J. Harlan Bretz. In the 1920s, Bretz was a high school biology teacher turned University of Chicago geologist who got obsessed with a weird part of eastern Washington. The locals called it the Scablands, because the ground looked like it had been scraped raw, not gently eroded, not smoothed by glaciers, but shredded. Bretz went out there on foot with paper maps and a measuring tape, and just started walking. Mile after mile of coulees, huge dry canyons with no rivers big enough to explain them. Basalt bedrock stripped bare, potholes the size of buildings, islands of rock that looked like they'd been attacked from all sides at once. Nothing about it fit the standard story geologists were telling each other at the time. Back then, the big idea in American geology was uniformitarianism, summed up in one slogan: the present is the key to the past. Rivers, rain, slow erosion, plus some glacial work during the ice ages. No need for sudden violent events. Catastrophes were considered sloppy thinking, the kind of thing pre-scientific people used to explain what they didn't understand. Bretz looked at the Scablands and saw something that laughed in the face of gradualism. He tried to make the standard tools work. Maybe these canyons took millions of years to carve. Maybe glaciers gouged them. Maybe normal rivers just somehow did way more than they do anywhere else on the planet. But every time he tested one of those ideas against the actual rocks, it broke. The valleys were too short and too steep for long, slow river erosion. The basalt surfaces were scoured, not gently polished like glacially carved landscapes. There were features that looked exactly like what you'd see on the bottom of a river. Bars, channels, streamlined islands, but scaled up to truly absurd sizes. He was forced to a conclusion he knew would be unpopular. This was flood terrain, not a bad spring runoff, not a once-in-a-century event. A gigantic, catastrophic flood that had ripped through the region with volumes of water far beyond any river on Earth today. So in 1923, Bretz did the scientific equivalent of walking into a room full of people who think they've solved a puzzle and saying, "Actually, you're all wrong." He published his observations, then presented them in person to the Geological Society of Washington, D.C. He described what he'd seen: dry falls hundreds of feet high that had clearly once carried waterfalls, huge scoured channels aligned, like branches of a single massive flow, bedrock stripped down to clean basalt over hundreds of square miles. He carefully avoided using the word catastrophe. He talked about extraordinary floods instead. But everyone in that room heard the C word anyway. The reaction was swift and frankly brutal. Senior geologists lined up to attack his interpretation. Some argued glaciers had done the work. Others proposed long-lived ice-dammed lakes draining slowly. A few suggested that maybe Bretz was just over-interpreting his field notes. The subtext was clear. We spent a century dragging geology away from biblical deluge thinking. We are not going back there because you saw some big potholes in Washington. Bretz didn't back down. He kept returning to the field, mapping more features, refining his argument. He pointed out that the supposed glacial explanations didn't match the directions of flow carved into the bedrock, that the scale of erosion demanded water moving at incredible speeds and depths, that the landscape looked like a frozen moment in a single, short-lived cataclysm, not a slow accretion of tiny changes. For decades the debate simmered. Bretz was treated as a kind of talented eccentric who'd gone a bit too far. Textbooks politely ignored his Spokane flood idea. The consensus held, yes, the Scablands are weird, but surely some combination of ice and time can handle it. The irony is that while Bretz was being dismissed as too flood-happy, another geologist was quietly uncovering the missing piece of his puzzle, upstream in Montana, evidence of a truly enormous ice-dammed lake that had once filled an entire valley system. A lake that, if its ice wall failed, could unleash more water than all the rivers on Earth combined for days. The full story of how that lake, Lake Missoula, turned Bretz from heretic to hero, and how it likely didn't burst once, but over and over, is where the Scablands story really starts to sound like something out of myth. That lake was Lake Missoula, and to understand what it did, you have to track the fingerprints it left behind on the land. Start in eastern Washington again, where Bretz had been wandering around, wondering what on earth had happened. One of the strangest things he kept tripping over were those coulees the locals talked about. A coulee looks like a river canyon that's lost its river. Huge, steep-walled troughs, sometimes miles wide, carved straight into solid basalt. Some of them have tiny streams trickling through the bottom today, like an afterthought. The streams are way too small to have done the carving. It's like finding a paper straw at the bottom of the Grand Canyon, and being told it did all the work. The most famous of these, Grand Coulee and Moses Coulee, don't bend and meander like normal rivers do when they've had time to wander across a landscape. They're blunt, direct, with cliffs hundreds of feet high and side canyons chewed out like someone took a fire hose to the rock. This is one of the first big clues that we're not dealing with normal water. Normal rivers evolve. They cut, they migrate, they build floodplains. The coulees look more like scars. They form a whole branching network, radiating out in the direction a massive sheet of water would have taken if it had been forced across the plateau and then dumped toward the Columbia. Now zoom out from those big gashes and drop down into the details. On some of the broad, flat surfaces between the coulees, Bretz and later researchers found something absolutely bizarre: ripples. Not little sand ripples like you see at the beach. Giant current ripples. Each one can be 20 or 30 feet high and hundreds of feet from crest to crest. An entire neighbourhood could fit between two of them. They're made of gravel and cobbles, not just sand, laid out in long parallel rows, all oriented in the same direction, like the bottom of a river that someone hit with an enlargement ray. And that's exactly what they are, bed forms. The same shapes water makes when it moves sediment along a channel, just operating on a totally different scale. You cannot get those with a trickle or with a normal floodplain river quietly overflowing its banks every spring. To move that much rock into wave trains that big, you need water that is deep, fast, and sustained long enough to reorganize the whole landscape. Think flows hundreds of feet deep, racing along at highway speeds. Those giant current ripples were one of the moments where alternative explanations started to break. Glaciers don't do that. Wind doesn't do that. Slow-draining lakes don't rearrange gravel into rhythmic megawaves over tens of miles. The only real candidate is a gigantic, fast-moving body of water that temporarily turned parts of eastern Washington into the bed of a super river. But the water didn't just sculpt the bedrock and pile up ripples. It also played UPS driver with some very large packages, scattered across the Scablands and beyond, sitting on hillsides and in fields like they were dropped from the sky, are big isolated boulders called erratics. They don't match the local bedrock at all. You can trace some of them back to rock types that only exist hundreds of kilometers away, up toward Montana and Canada. They're often perched on top of fine sediments or sitting alone on otherwise uniform basalt. No obvious landslide above them. No cliff they've fallen from. Just huge rocks in the wrong place. Glaciers are famous for leaving erratic boulders behind as they melt, and for a long time that was the default explanation. But here's the twist. The sizes, locations and rock types of a lot of these erratics line up beautifully with the idea of icebergs riding on top of a flood. Picture Lake Missoula when it was full, a deep, icy lake dammed by a tongue of the Cordilleran ice sheet. Chunks of that ice would carve off and float in the lake, carrying rocks scraped from distant valleys. When the ice dam finally gave way and the lake emptied, those bergs would have been swept out with the torrent, bobbing along in water hundreds of meters deep. As the flood roared across Idaho and Washington, some of those ice rafts would have grounded on high spots or stalled in eddies. As they melted, they dropped their cargo. That's how you get a lone granite boulder from Montana, calmly sitting on a ridge in the middle of Washington basalt country. In some places, you even see clusters of erratics scattered across hillsides, like the breadcrumbs of a dying iceberg trail. Combine that with the giant current ripples underfoot and the coulees gouged into the bedrock, and a single picture starts to come into focus. An enormous body of lake water, released all at once, thundering west as a temporary inland sea in motion. Individually, each of these landforms could maybe be explained away. A weird canyon here, some odd ripples there, a few misplaced boulders. Together they form a coherent story, a landscape where flow directions, erosion patterns, sediment structures, and stray rocks all point the same way, downstream from a vanished lake that must have been truly enormous. And that still leaves the most unnerving question hanging in the air. If a lake that big could fail once, how many times did it fail? And what did that mean for everything living in its path? The first instinct when you see a landscape like that is to assume it was made by a one-off catastrophe. One bad day, one apocalyptic failure of the ice dam, one wall of water, and done. But the rocks refuse to give us that kind of simplicity. When geologists started really mapping the Scablands in detail, they kept running into something inconvenient. If you're a fan of one-and-done disasters, layers. Not just one blanket of flood sediment smeared over the lowlands, but stacks. Packages of sand and silt and gravel lying on top of each other like a pile of dirty blankets, each one telling the story of a different flood. You see it best in the quieter zones, the places where the water slowed down. When that super river burst out of Lake Missoula and tore across the Columbia Plateau, it didn't stay raging everywhere at once. In some basins and side valleys, the flow pooled and spread out, forming temporary lakes of brown, churning water. As the current slowed, the heaviest stuff, boulders and cobbles, dropped first. Then, as the water got calmer, finer and finer sediments settled on top, like dust in a room after a storm. Now here's the key. In many of those basins, you don't just see one tidy, fining upward package. You see multiple coarse at the bottom, finer higher up, then a sharp break. Sometimes a bit of soil or faint weathering, then another coarse pulse, then finer, again, over and over. That pattern screams repetition, flood, pause, flood again. In some places you can even count them. Around the margins of what used to be Lake Missoula and down in the big valleys that acted like bathtubs along the route. Geologists have identified dozens of distinct flood layers, 40, 60, in some interpretations even more than 100 separate deposits. Each one implies the same basic sequence. The lake filled, the ice dam failed, a surge of water blasted out, the floodwater ponded and dropped its load of sediment, the system calmed down, and then the lake started filling again. The ice dam was not some delicate thing that shattered once and never recovered. It behaved more like a flimsy door in front of a very determined river. The Cordilleran ice sheet kept advancing into the Clark Fork Valley, plugging it, and snow kept falling on the mountains, feeding the basin. Water built up behind that ice plug, until the pressure got too high, or warm water undercut the base, or cracks propagated through the ice. Then failure. Lake drains catastrophically. Ice tongue retreats a bit, the dam is gone, and the process starts over. This isn't just theory. You can actually see the old shorelines of those refill cycles. Around the hillsides of western Montana and northern Idaho, there are faint horizontal lines etched into the slopes, strand lines, ancient beaches. They form a staircase of high water marks at different elevations, evidence that the lake didn't always reach exactly the same level before it let go. On some terraces you find beach gravels perched hundreds of meters above modern river level, with different weathering states and fossil content. Some are fresh, others are more altered, hinting at the passage of time between separate episodes of inundation. Downstream, the story repeats in a different accent. Those giant current ripples you saw in the last section. In certain fields and valleys, they're not all exactly the same age. Careful work shows sequences where younger ripples partly overrun, or cut into older ones, like a second set of waves marching over the fossilized pattern left by a previous storm. Even the erratics carry the signature of multiple journeys. In places you see more than one train of foreign boulders at different heights, associated with different sediment packages. That's much easier to explain if icebergs were being flushed through the system again and again, dropping cargo at different flood stages. And then there are the loess and soils. Between some flood layers, especially farther from the main current, you find thin bands of wind-blown dust and even fragile soil horizons, places where plants had started to grow, roots had begun to work through the sediment, and the surface had time to sit quietly under the sky. You don't grow a recognizable soil in a week. That means the interval between some floods wasn't measured in days or months, but in decades, maybe centuries. Long enough for people and animals to move back into the valleys, for hunters to learn the safe crossings, for children to grow up hearing stories about the time the water came. Then, without warning from a human perspective, it would happen again. Imagine living on those rhythms. If you date some of these layers with techniques like radiocarbon on organic bits or luminescence on the grains themselves, they point to a pattern stretching across thousands of years toward the tail end of the last ice age. Lake Missoula didn't just blow once and vanish from history. It likely cycled through this fill and purge behavior over and over as the climate swung and the ice sheet advanced and retreated. Some estimates suggest an average repeat time on the order of decades to a century or two between big outbursts, with total numbers of major floods possibly in the dozens. Enough that, if humans were in the wider region, whole cultural traditions could have been shaped under the long shadow of the next flood. And the megafloods didn't just leave their mark in eastern Washington. Follow that water farther west, down the Columbia, and you find more quiet witnesses waiting in canyons and valleys that most people drive through without a second thought. If eastern Washington was the demolition zone, the lower Columbia and the Willamette Valley were the archive. Out on the Scablands, the water was doing insane work, ripping rock out by the cubic kilometre, sculpting coulees and cataracts. But by the time those floods squeezed through the Columbia Gorge and spilled into Oregon, the energy story changed. The canyon narrowed, the river turned, the floodwater piled up and slowed down. And when water slows down, it starts to talk in layers. Think about what those outbursts really were. Not just big versions of today's Columbia, but pulses of water hundreds of meters deep, jammed with icebergs, trees, soil, even chunks of other landscapes. When that torrent hit the choke point of the gorge, it couldn't all rush through at once. Some of it backed up like traffic at a tunnel. The first clue to this backup are the high-level deposits clinging to the walls of the gorge. Geologists hiking along modern road cuts and canyon slopes have found neat, flat-topped benches way above the present river. On those benches, packages of fine-grained sediment, sand, silt, sometimes delicate laminations that only form in calm water. Mixed into them, weird things, isolated pebbles and cobbles dropped like sprinkles into a cake. Those out-of-place chunks give the game away. They're drop stones carried in by ice rafts and released as the ice melted. To get drop stones sitting in quiet, fine lake mud, hundreds of meters above the modern river, you need something very specific, a gigantic temporary lake filling the gorge during a flood, with icebergs floating overhead. Geologists call these still water accumulations slackwater deposits. They show up downstream in a repeating pattern, in alcoves and side canyons that would have been sheltered from the main jet of current. You see the same story over and over, a sharp base cut into older material, then a pulse of coarser sand, then finer and finer layers as the water calms, sometimes capped by a bit of weathering or soil, and then the whole sequence starts again, stacked like a layer cake on the canyon walls. You can almost feel the hydrograph in those rocks. Flood surges into the gorge, water level climbs, turbulence gradually dies away, mud rains out of suspension onto the quiet margins. Then the lake drains, everything dries, life creeps back in for a while, until the next Missoula flood jams the system, and the gorge fills again. The gorge was just the first reservoir. Farther west, where the Columbia finally punches out of the mountains and spills into the lowlands of Oregon, those temporary lakes grew enormous. During the largest floods, the water surface didn't just nudge up a few meters. It rose hundreds of feet above present sea level, flooding what is now Portland, and pushing south into the Willamette Valley for more than 100 kilometers. Imagine the Willamette not as a gentle agricultural valley, but as an arm of a temporary inland sea. The floodwater pouring out of the gorge hit the open lowland, spread laterally, and lost speed. Overnight, well, over a few days, the Willamette became a broad, murky lake. Trees and soil ripped out of eastern Washington floated here. Icebergs carrying boulders from Canadian bedrock bobbed on its surface. Thick, sediment-laden water slowly cleared as the heaviest grains fell out first. Today, if you dig into the valley walls and terraces around places like Salem, Albany, or even Eugene, you find the ghost of that lake. There's a distinctive blanket of pale, fine-grained silt and very fine sand draped across much of the lower Willamette Valley, a unit geologists call the Willamette Silt or Willamette Formation. It's not the kind of stuff local rivers usually drop. It's too clean, too uniform, spread too widely and perched at elevations that only make sense if the entire valley floor was once underwater. Inside that silt, you see the same slackwater signatures as in the gorge. Delicate, horizontal laminae that would have been shredded by strong currents. Occasional sharp contacts between packages, telling you one calm water episode ended abruptly and another began later. And again, drop stones, lone pebbles and cobbles of exotic rock types that have no business being embedded in Oregon mud unless they fell out of melting icebergs. Some of those erratics are so large they become landmarks, basalt boulders from eastern Washington, or granites from far to the north sitting on hillsides miles from any plausible local source. Many of them rode in on icebergs that drifted over the drowned Willamette Valley, then were beached and stranded as the temporary lake drained away. Here's the pattern that ties everything together, the elevations. If you map out the highest level where these slackwater silts and scattered erratics appear, In the gorge around Portland up the Willamette, you get a contour line, a bathtub ring. It traces the maximum water surface reached by the largest floods. But it's not just one bathtub ring. In cross-sections along the valley, you can see multiple benches of silt at different heights, multiple sets of slack water layers separated by breaks and soils. Just like upstream, the Willamette Valley records not a single apocalyptic filling, but a series of lake episodes, some higher, some lower, over thousands of years. Each Missoula outburst turned the gorge into a temporary reservoir, and the Willamette into a drowned valley. Each one laid down another quiet layer of mud, another scattered cargo of ice-borne stones. Then the water drained out, leaving behind a strangely fertile silty floor. That detail turns out to matter for humans much, much later, because those flood-built silts are exactly what made the Willamette one of the richest agricultural regions in North America, a place where later peoples would thrive, and where stories about the water's power would settle as deeply into culture as the sediments did into the soil. And that brings us to the people. It's one thing to reconstruct the hydraulics and the mud. It's another to ask what it would be like to live in a world that could do this, and how memories of such a landscape-scale temper might echo in myths of floods that seemed, from a human vantage point, to drown the whole earth. So let's zoom the camera down now. Forget the satellite view of whole basins, filling and draining. Put yourself in a single village, in a single valley, where lives are measured not in ice ages but in harvests and winters. The biggest Missoula floods were done long before any humans set foot in the Pacific Northwest. The classic outburst sequence wrapped up around 13,000 to 15,000 years ago. The earliest clear archaeological traces of people in that region are younger. So no, there were no humans standing on the hills above Spokane watching a 2,000-foot wall of water race by. But that doesn't let these floods off the hook when it comes to myth-making, because geology isn't a single event, it's a habit. Once you learn what a landscape is capable of, it tends to repeat itself at different scales, in different guises, long after the original cataclysm is over. Take the coast and interior Salish, the Chinookan peoples along the lower Columbia, the Kalapuya, and other groups in the Willamette Valley. By the time they were shaping rich oral traditions about floods, animal people and world reshaping waters, the ice sheets were gone. The Great Missoula Dam was just a memory written in bedrock, but the effects of those megafloods were everywhere. They lived on the fertile silts poured into their valleys by ancient lakes. They fished in rivers diverted and deepened by those old torrents. Their villages sat on high benches carved by catastrophic flows, or on gravel bars abandoned when the water finally calmed. In other words, their daily life was literally built on the consequences of floods so large they almost defy imagination. And the landscape itself kept telling the same kind of story, over and over on more human scales. Rivers still rose and fell dramatically with seasonal melt. Landslides slumped off oversteepened scabland cliffs. Local outburst floods burst from glacial or landslide-dammed lakes in the mountains. Tsunamis from Cascadia megathrust quakes slammed the coast every few centuries. You don't need a 2,000-foot wave to make a culture take floods extremely seriously. A river that jumps 20 meters in a night, or a coastal surge that rips forests out by the roots, will do the job just fine. Now add something else. The evidence of a world-scale drowning literally lying around you in plain sight. Imagine you're a fisher on the lower Columbia 1,000 years ago. You know every bend in the river. Every rock has a name. Every beach has a story. But scattered across the valley are these bizarre boulders of alien stone. Granites that match nothing in the local hills. Dense basalts you only ever see far upriver. Some of them big as houses, perched alone in fields like they were gently placed there by a giant hand. You ask your elders, how did that stone get there? They don't have glaciology or paleohydrology. What they have is observation and memory. Well, child, stone does not walk. It does not float. Only water carries things that heavy. So if that rock sits that high above the river, the water must once have risen that high. From that perfectly rational inference, you get a perfectly rational conclusion. At some time in the deep past, the water had covered everything you can see. And remember those benches of slackwater silt cropping out high on the valley walls? To a geologist, they're quiet deposits from a temporary Ice Age lake. To a person farming or foraging below, they're a line around the hills, a literal mark of where the water once reached. A bathtub ring on the landscape is a powerful visual metaphor. You don't need instrumentation to read it, you just point and say, "See that line up there?" That's how high the water came in the ancient flood. This is how you end up with flood stories that sound global, even if the event was only global within a person's horizon. If all the land you know is one valley and a stretch of coast, and that entire world goes under water, then the whole world has been drowned. If everyone you know has to flee to the hills, then all people have been saved on the heights. Scale is relative. Myths faithfully preserve the emotional truth of catastrophe, not the hydrological boundary conditions. And the Missoula story shows something else, subtle but important. You don't need one perfect once and for all apocalypse to generate enduring flood legends. A series of big, scary landscape, shaping floods spread out over thousands of years, will do just as well, maybe better. Each generation encounters some version of the water's power. A year when the river eats a village site, a winter when the lowlands become a lake, a quake-driven wave that tears through a coastal estuary. Each event plugs into an older framework of stories about a time when the water rose higher than anyone could see. The geology gives you the raw material. Over-deepened canyons, stranded boulders, silt-capped terraces. The lived experience adds the immediacy, sudden inundations, lost homes, miraculous survivals. Oral tradition weaves both together into a coherent narrative about cycles, warnings, and the dangerous generosity of the water. From a scientific standpoint, the Missoula megafloods are intensely local. One region, one ice margin drainage, one chapter in the end of the last ice age. They didn't touch Africa or India or Australia, but as a pattern, they're anything but local. They show us that ice ages end in pulses, not in smooth gradients. Ice sheets and glaciers love to form temporary dams, and temporary dams love to fail. When they do, they rearrange entire regions in days and leave behind clear, baffling clues for whoever comes later. Now imagine dozens of separate regions around the world, each experiencing their own versions of this as the last glacial period unravelled. North America has Missoula and its cousins. Northern Europe has its Jokullaups and Baltic floods. Asia has its outburst lakes. Coastal peoples everywhere face sudden sea-level jumps and storm surges, supercharged by a changing climate. Nobody needed to watch a single planet-wide ocean surge over Mount Everest to start telling stories about a great flood. What humans did see, again and again in different places and times, were waters that rose faster than you could walk, that erased familiar landmarks, that turned whole homelands into lakes or seafloors. Missoula's Scablands are just one of the sharpest, most legible case studies of how violent those changes can be, and how indelibly they mark a land. By reading that stone record, we don't just reconstruct an Ice Age plumbing problem. We see the kind of episodes that would, in any culture, crystallize into tales of divine anger, moral resets, or world renewals by water, and once you understand that, it becomes easier to see flood myths not as garbled reports of a single supernatural event, but as a collage, a global scrapbook of real catastrophes like Missoula's, stitched together across continents and millennia. The Channeled Scablands whisper that story in rock. Other places shout it in shorelines, coral reefs and drowned forests. To hear those other voices, we have to step beyond rivers and inland seas and look at what happens when the ocean itself lurches upward in a geological instant. Fourth on our list is what might be the closest thing science has found to a global flood that actually deserves that name: Meltwater Pulse 1A. Rapid sea level rise around 14,600 years ago. Not a single wave, not a Hollywood wall of water, but something in some ways even more unsettling. The entire ocean surface of the planet creeping steadily upward, decade after decade, faster than most coastlines could adapt. To get a feel for what that means, we have to shift scale again. Forget one river jumping its banks. Forget one inland basin filling up. Picture every shoreline on Earth moving inland. Not by the width of a beach, but by miles. Continental shelves turning into seafloor, low-lying plains turning into estuaries, islands shrinking, merging or vanishing. And the wild part is, we're pretty sure this happened within the span of a few human lifetimes. So what was Meltwater Pulse 1A exactly? At the end of the last ice age, huge ice sheets still covered North America, Northern Europe and parts of Asia. Global sea level was lower than today by more than 100 meters. That means the world's coastlines looked completely different. Broad continental shelves exposed land bridges connecting regions that are now separated by water, river valleys extending far out where there's only ocean now. As the climate warmed, those ice sheets started to retreat. In general, sea level rose slowly over thousands of years. But on top of that slow background trend, scientists see abrupt spikes. Short windows where sea level didn't just rise, it jumped. Meltwater Pulse 1A is the sharpest of those spikes. Depending on which reconstruction you look at, it added somewhere on the order of 12 to 20 meters of sea level in only a few centuries. Some estimates put the fastest phase at something like 3 to 5 meters per century. Translate that into something a coastal villager might notice. Every 20 years, the high tide line creeps inland by several human heights. For a community living right on the edge, the difference between one lifetime and the next could be the difference between the sea is out there and the sea has taken the old village. But how do we know this happened? Nobody was out there 14,600 years ago sticking rulers in the surf. This is where the ocean hides one of the most remarkable natural archives we have: coral reefs. Unlike myths, corals actually keep timestamps. Many coral species that build reefs in the tropics are picky. They want to live close to the surface, in the sunlit, warm, shallow zone where light is strong enough for their symbiotic algae. Too deep, and they starve, too shallow and exposed, and they bleach or dry. So as sea level changes, coral reefs either drown or chase the surface upward. They grow in layers, building vertical stacks of limestone that roughly track where sea level used to be. Think of them as living tide gauges that got turned into rock. When scientists want to reconstruct past sea levels, one of the first places they go is ancient reef terraces, fossil coral platforms now stranded above or below the modern sea surface. Drill a core down through those terraces, and you're basically extracting a time column of former sea level positions. Each fossil coral you pull out grew at a particular depth relative to the sea surface. Radiometric dating, especially uranium-thorium methods, can pin down when that coral was alive, often to within a few hundred years. Do this in enough places, on enough reefs, and a pattern emerges. Around 14,600 years ago, you see whole reef systems forced to grow upward at breakneck speed, or else drown. You see stacked coral communities that, based on their ecology, should each have had plenty of time to spread out, but instead are piled one atop the other, compressed in time. That compression is the coral's version of panic. The sea surface above them is rising so fast that they can barely keep up, even though some corals can grow more than a centimetre a year under good conditions. For a reef ecosystem that's like sprinting, and in multiple regions, the Caribbean, the Indian Ocean, the Pacific, the radiometric dates cluster in the same narrow window. Corals that lived at near sea level depths on different sides of the planet all show an abrupt shift, a stair-step jump, right around that 14.6 thousand year mark. This is one of the lines of evidence that let geologists say something global was happening to sea level, not just a local crustal wobble or a regional uplift. Corals aren't the only record along coastlines that were tectonically relatively stable. You can find ancient beach ridges, tidal flats, mangrove peats and shell beds that formed right at or near past sea level. As the ocean rose, it left behind a whole ladder of these features. In some places, these coastal deposits now lie inland and above current sea level, because the land has gently flexed or because long-term isostatic rebound has lifted them. In other spots, they're below present sea level and only show up in sediment cores or seismic profiles. Either way, their ages can be measured. Carbon-14 dating can be used on shells, plant material and organic mud. Uranium series can date carbonate formations. When you line these ages up against their depths and positions, you get an independent curve of how relative sea level changed at that spot through time. Now, here's the key. When researchers from different countries started compiling these local curves, they noticed that many of them showed kinks, points where the slope of the line suddenly steepened, right around the same age that coral reefs were freaking out. Shoreline peats suddenly shift from freshwater to brackish to fully marine over just a couple of layers. Beach deposits jump landward, drowned river valleys show a rapid deepening recorded in their sediment fill. None of these single observations prove a global jump by themselves. Each one could in theory be explained by local subsidence, an earthquake, or some other regional effect. But when coral terraces in Tahiti, reef stacks in Barbados, coastal deposits along the Sunda Shelf, and cores from drowned continental margins all start humming the same tune. A rapid rise, starting around 14,600 years ago. It gets hard to blame it on local quirks. The simplest explanation is that the thing common to all of them, the global ocean, changed. Of course, the ocean doesn't write its diary in plain language. The curves are noisy, different sites respond differently, depending on how flexy the crust is, how close they were to the big ice sheets, how local currents moved sediment around. So a huge amount of work goes into teasing a clean eustatic sea level history, the true global signal, out of this messy patchwork of local records. That's where the sea level curves you sometimes see in textbooks come from. Careful statistical mashups of coral ages, coastal geomorphology, deep sea sediment data, and models of how the Earth's crust and gravity field respond when you shift that much water around. And right there, in almost every reconstruction, is a cliff face in the curve at about 14.6 thousand years ago. Meltwater Pulse 1A. An interval when, for reasons we'll get to, the planet's frozen water decided to move fast from land to sea, and every coral, every estuary, every low-lying shore had to deal with the consequences. Now it's one thing to talk about coral curves and eustatic sea level. It's another to imagine what this would have meant for actual people whose homes sat on those vanishing shorelines. Because by 14,600 years ago, we're not dealing with scattered bands of near-extinct hominins anymore. We're dealing with fully modern humans who had already survived an ice age, learned its patterns, and built entire ways of life around the coastlines that existed then. And those coastlines were enormous. Drop global sea level by 100+ meters, and the world grows new land. Continental shelves become wide coastal plains. River mouths sit far out where we see nothing but waves today. Places like the North Sea, the Sunda Shelf between Southeast Asia and Australia, and the exposed bed of what's now the Persian Gulf weren't seas. They were dry ground, with rivers, lakes, wetlands, and most likely people. Archaeologists sometimes call these now drowned regions lost landscapes, but to the people living there, they were just home. Imagine one of those plains. Out where your modern map says continental shelf, there's a ribbon of fertile land following a river to what is now the edge of the drop-off. Slightly inland, broad grasslands, farther back, hills and forests that in your time are called the mainland, but to you are just the uplands you visit seasonally. If you're a late Pleistocene forager, this kind of place is a jackpot. Rivers concentrate fish and shellfish. Wetlands attract birds, migrating herds follow predictable routes, and the gentle topography may give you rich soils for wild grains and tubers. You don't need cities or farms for this land to be crowded. Crowded at this point in history might mean a few dozen small bands within a day's walk of each other, regularly meeting to trade, find partners, and share information. Now introduce Meltwater Pulse 1A into that system. The first thing you notice isn't a towering wave, it's nuisance flooding. A camp you used to use every dry season suddenly has a muddier shoreline. A sandbar you knew as a shortcut between two bends in the river begins to sit underwater more often. At first this is just annoying. You move camp a little higher. You rebuild your fish traps a bit farther inland. You shrug and blame it on a wet year. But your elders start talking, because they remember when that old shell midden inland really was on the beach. They remember when the tidal channel you now cross by canoe was a marsh you could walk through, carefully at low water. They have stories they heard from their elders about another campsite, even farther out, that the sea took when they were children. In other words, by the time Meltwater Pulse 1A is fully underway, people are already living in a world where the shoreline has been inching inward for generations. The difference now is speed. Every decade or two, a flood that used to be once in a lifetime starts happening more often. The high tide line, which used to stabilize more or less in the same place, now keeps edging upslope. Trees along the coast develop rotten, salt-burned roots. Freshwater springs turn brackish. If your life depends on specific shellfish beds, certain reed patches, particular crossing points for migrating animals, these are not abstract problems. They are existential threats. So, what do humans do when the sea won't stop following them? They move, but they don't move into an empty world. Remember that during the last glacial maximum, huge swaths of inland terrain were cold, dry, and relatively low in productivity. As the climate warmed, those zones began to green, but that didn't happen uniformly. Some valleys became lush early, others lagged behind. Groups already living in the uplands had first pick of the newly pleasant landscapes. They knew the terrain. They knew where the good springs, caves, and hunting grounds were. They had attachment to specific hills, cliffs, and groves that had sheltered them through harsher times. When coastal groups began pushing inland, they were pushing into territories that often already had owners. You can see where this is going. Meltwater Pulse 1A didn't just erase land, it squeezed people together. It took populations that had been stretched across wide coastal shelves and funneled them, step by step, into narrower belts of habitable ground. Think about some specific regions we know were transformed. Where the North Sea is now, there used to be a sprawling lowland archaeologists called Doggerland. It connected what is now Britain to mainland Europe. Rivers crisscrossed it. There were lakes, marshes, and gently rolling hills. Mesolithic tools and submerged peat deposits tell us people lived there for thousands of years, hunting, fishing, and likely moving seasonally between low and high ground. As sea level climbed, that plain didn't vanish overnight. It shrank. The outer edges drowned, turning into broad estuaries. Inland settlements that had always been safe became seasonally flooded. Paths between groups were cut by widening channels. What had been a continuous land bridge turned into a maze of peninsulas and islands, then a scattering of shrinking hilltops, and finally nothing but shoals. At each stage people had to decide, stay and adapt a little longer, or pull back and abandon yet another piece of their world. The Sunda Shelf, stretching between what is now mainland Southeast Asia, Borneo, Sumatra, Java, and the Philippines, tells a similar story. Lower sea levels once tied these land masses together into a big Pleistocene subcontinent known as Sundaland. Genetic and linguistic evidence suggests this region was a thriving cradle of human populations, with roots extending toward what would eventually become Australia and New Guinea. As the ocean rose, Sundaland fragmented. River basins that had been inland became drowned valleys. Coastal plains turned into shallow seas. People who had moved between regions on foot or by short canoe hops suddenly needed longer voyages, better boats, and new mental maps of where the land actually ended. All of that means one thing: migration pressure. Some of that pressure was gradual. Families making the calculation that their children will have an easier time if they marry into a group farther uphill. Bands deciding to shift their seasonal rounds inland a little earlier each year. Traders choosing safer routes that avoid the increasingly unstable coastal fringe. But some of it would have been acute. Storm surges reaching farther than anyone remembered. A river mouth catastrophically reorganized by an especially high flood, wiping out camps, freshwater sources and boat landings all at once. An epidemic sweeping through a low-lying wetland community whose people had few immunities to diseases common inland. Events like that can tip a slow, reluctant retreat into a sudden exodus. Now imagine what that looks like from the perspective of the people already in the interior. Every few years, new faces appear along the edges of your territory. They speak a slightly different dialect. They know different fishing techniques. They bring shell beads from coastal species you've never seen alive. They're desperate for access to your springs, your animal drives, your sacred groves. Sometimes this ends in alliance, intermarriage, shared camps during lean seasons, exchange of knowledge, coastal groups teaching interior groups new ways to exploit rivers and wetlands, upland groups sharing fire regimes or plant lore tuned to their hills. Sometimes it ends in violence. A hunting ground that once fed one band now has to support two. A formerly unclaimed valley, suddenly critical as the last patch of good land between the mountains and the encroaching sea becomes worth fighting over. A bad year of rains hits at the same time, another slice of the coastal plain goes under, and the fragile balance between sharing and defending breaks. This is one of the underappreciated ways a rising ocean can shape human history. Not just by drowning land, but by jamming people into tighter spaces and forcing them to renegotiate who belongs where. And all of this is happening on a planet where climate is still jerking back and forth between colder and warmer pulses, where animal ranges are shifting, where big river systems are recarving their channels in response to the changing base level at the coast. From the inside, living through it, you wouldn't say, yes, we are currently experiencing Meltwater Pulse 1A, a eustatic sea level rise event. You'd say something closer to, the sea has been coming for us since my grandfather's grandfather, but in my lifetime it has eaten more land than anyone remembers. The people from the drowned low country have arrived, and there is nowhere left to go that does not already belong to someone. Hold that thought, because it's in that kind of pressure cooker, slowly rising water, shrinking land, converging populations, that certain types of stories start to crystallize and get passed down. So how do you turn all of that slow, crushing pressure into a global flood story? You start with memory, but not just one person's memory. Layered memory. Think about what old means in an oral culture. You don't have books. You don't have archives. You have people. And the past is as long as the chain of people whose words you still trust. Your grandmother remembers the last time the water jumped suddenly, when the camp by the old sycamore finally went under for good. Her grandmother remembered when there was still a sandbar out, where now there's nothing but whitecaps. Trustworthy memory probably runs 3, maybe 4 generations deep. After that, you're in the realm of story. But story in that world isn't just story. It's also data storage. If your group has been tracking the shoreline for 500, 800, 1,000 years, you're not remembering each individual meter of retreat. You're compressing that whole drawn-out disaster into a few vivid, teachable moments. The summer the river split, and half the village was swept away. The night the lights came from the sea, and the thunder never stopped, and in the morning the land where our people were born was gone. My ancestor tried to outrun the waters and climbed a hill until his legs could not carry him, and still the waves climbed higher. Take those kinds of episodes, the worst storm in 200 years, the freak combination of high tide and meltwater surge, the big estuary collapse that takes a dozen people at once, and pack them together in narrative time. That's how you get a day when all the world went under. Because all the world, from your point of view, is not the planet. It's the basin you can walk around in a season. It's the plain your trade partners visit. It's the coast you've actually seen with your own eyes. If every low valley you've ever known is now marsh, and every further valley you've only heard of is also said to be drowning, all the world is disappearing, even if some distant plateau is doing just fine. And remember what kind of coastlines we're talking about. These aren't steep, rocky shores where a metre of sea level change just makes the waves slap a little higher on the cliffs. These are low, shallow shelves where a modest vertical rise eats huge horizontal distances. From a forager's perspective, that can absolutely feel like the sea suddenly leaping forward, devouring villages that thought they were safe. Maybe not in a single afternoon, but in the compressed, moralized space of narrative. All the small retreats and smaller panics get folded into one big, definitive catastrophe. Now zoom in on what happens to cultural identity when your literal ground disappears. For generations, your group has been the people of the river mouth, the children of the wide marsh, those who live where the 3 rivers meet. Your name, your gods, your origin stories are anchored to specific landforms. The hill where the first fire was stolen, the pool where the ancestor came out of the underworld, the sand spit where the trickster turned into a bird. Meltwater Pulse 1A doesn't just erase camps, it erases reference points. The sacred boulder is now 10 meters offshore. The ancestral cave is flooded to the ceiling. The burial ground that proved your claim to this place is under salt water. What do you do as a storyteller when the places that define who you are no longer visitable? You pull them inland into myth. You say, before the world was as it is now, when our land was wide and the sea was further away, our ancestor did such and such on that stone. You explain the missing geography by giving it a reason to be gone. Human wickedness, divine anger, broken taboo, cosmic accident. Anything but the physics of ice sheets. At the same time, you're not the only one doing this. Every group being squeezed inland is having some version of this experience. Different languages, different gods, different hills. But the same pattern. We used to live where the sea is, we had to leave. It was bad. Now they're meeting each other. Around campfires, in the new crowded interior corridors, people swap origin stories the way they swap tooltips and marriage partners. And they notice something uncanny. Your elders also say the sea took your first village. Your gods also drowned your bad ancestors. Your people also escaped on a boat, or to a mountain top, or by following a bird. Patterns like that are what make myths feel universal, not just local. Once you have a shared template, a time when water covered everything, when only a few survived, when the old world ended and a new one began, it becomes a flexible framework. You can plug in your own geography, your own heroes, your own moral lessons. It stops being just a description of one flood and becomes a way to think about any overwhelming loss. Fast forward enough generations, and what started as very literal, very local memories of shorelines creeping inland have been retold through multiple climate swings, multiple migration pulses, multiple smaller floods and tsunamis riding on top of the long, slow melt. Each new crisis gets mapped onto the old template. A bad monsoon season that wipes out crops, like the days when the great waters came, a regional lake overtopping its banks and tearing through a valley, like in the time of our ancestor who escaped the flood, a later tsunami hammering a coast already narrowed by sea level rise. That one practically demands to be folded into the master story, not just a flood, but the flood. This is where you can imagine something like Meltwater Pulse 1A, acting as a kind of deep background radiation in human storytelling. Even when the exact events are no longer clear, the structural memory is there. The world used to be bigger. The waters rose. Many died. A remnant survived by climbing, by building, by listening to a warning. Across thousands of years and tens of thousands of kilometers, that skeleton of a story is robust enough to survive translation, migration, conquest, and religious revolution. But that doesn't mean every flood myth on Earth traces back to this one meltwater pulse. Human communities have seen plenty of other ways water can ruin your day. And some of those later, more specific disasters may have fused with this older template in surprisingly direct ways. And that brings us to an awkward question scientists are still wrestling with. How much of this background radiation story really belongs to that one big jump, and how much is us smoothing over a messier, lumpier reality? On the physical side, Meltwater Pulse 1A looks clean in the graphs. You see a relatively flat line, then a sharp, steep climb. Boom. 20 meters or so of global sea level rise crammed into a few centuries. But the closer scientists look, the less it behaves like a single neat event. First problem, where did all that water actually come from? You've got two main suspects, and they both have alibis. One is the collapsing ice sheets in the northern hemisphere, especially the Laurentide ice sheet that used to smother most of Canada and part of the northern US. If that monster lets go of a few big sectors, the ocean rises. The other is Antarctica. There's growing evidence that big marine-based sectors of the Antarctic ice sheet, ice grounded below sea level, can destabilize fast when the surrounding ocean warms. Think of it like knocking the legs out from under a table. If you ask some glaciologists, the North did most of the work. Huge proglacial lakes in North America, ice-dammed reservoirs like an earlier, even bigger version of Lake Agassiz, may have drained suddenly when their icy walls failed, dumping fresh water into the North Atlantic and raising sea level. Ask a different camp, and they'll tell you Antarctica had to be the main driver. Coral data from places like Tahiti and Barbados suggest the pattern of sea level change, which places rose faster, which slower, fits better if a lot of the mass loss happened in the south. Then you get the compromise models. Maybe it was both, with the north and south taking turns coughing ice into the sea over a few hundred years. The reason they're still arguing is that none of our tools are fine-grained enough to give a simple, "it was this on this exact day" answer. Those lovely sea level curves you see in textbooks, they aren't thermometers dipped into the ocean at regular intervals. They're reconstructions stitched together from coral reefs, drowned shorelines, sediment cores, and computer models of how Earth's crust flexes when you move trillions of tons of ice and water around. Corals give you especially good snapshots. Some species only grow within a narrow band of water depth, right near the surface. If you find an ancient coral terrace now sitting 30 meters below modern sea level, and you can date when it grew, you get a data point. Sea level at least passed through that depth at that time. But a data point in this world is not a GPS coordinate. It's a fuzzy blob. Radiocarbon and uranium-thorium dating come with uncertainties. Plus or minus a couple hundred years here, 500 there. When you're trying to resolve something that might have unfolded over, say, 3 or 4 human lifetimes, those error bars are enormous. Then there's the geography problem. Sea level is not like filling a bathtub. The planet is lumpy and elastic. When an ice sheet melts, the crust underneath slowly rebounds, like a memory foam mattress after you stand up. Gravity fields change as you move mass from land to ocean. Water piles up higher near some coasts and sits a little lower near others. So when you compare a coral record from the tropical Pacific to a drowned marsh in the North Sea and a raised beach in Antarctica, you're not seeing one simple global curve. You're seeing local versions of a global story, each warped differently by crustal rebound, tectonics and gravity. To turn that into a single Meltwater Pulse 1A line, scientists have to peel off all those local distortions with models. Those models are good, but they're not perfect, especially when you go back tens of thousands of years, and the exact shape of ancient ice sheets is itself partly guesswork. Add in the fact that different dating methods sometimes disagree by a few hundred years, and you end up with overlapping scenarios that can't yet be cleanly separated. One timeline might say, big northern lake outburst first, quick sea level jump, climate hiccup, then a slower Antarctic contribution. Another might say, a long sustained Antarctic bleed, with shorter northern pulses riding on top. Both can fit the existing data within error margins. Both produce graphs that to a non-specialist look like a sudden step. And this is where the scientific and mythic problems start to rhyme. On the ground, for actual people living through it, you don't experience global mass balance of ice sheets. You experience local relative sea level. Did it rise faster this lifetime than your grandfather's? Did the river mouth you grew up on become an estuary by middle age? Did the big storm of your youth reach farther inland than any storm your elders remembered? If the global curve we draw today smooths 3 or 4 distinct bursts of meltwater into one big uptick, oral tradition likely does something similar in the other direction. It compresses multiple coastal disasters into one world-ending flood, or stretches a single intense generation of loss into a whole age of drowning. From the perspective of physics, it matters a great deal whether 10 meters of sea level rise came mainly from Antarctica or mainly from Canada. It changes how we model future collapse risks, how we think warm water eats at modern ice shelves, how we calibrate climate sensitivity. From the perspective of a forager watching their coastline vanish, those nuances are invisible. All you know is the sea came in faster than our stories said it would. Our maps of who we are stopped matching the land. The old places disappeared. We moved and we met other people whose elders said, yes, it happened to us too. So when you see a clean, sharp step in a sea level curve labelled Meltwater Pulse 1A, remember 2 layers of uncertainty. Underneath, scientists are still arguing about exactly which ice sheet did what, in what order, and how fast. On top, human storytellers have been blurring together centuries of local floods, storms, and shoreline collapse into a few powerful narrative beats for at least as long. Somewhere in between those two approximations, the smooth curve and the smooth myth, sits the real experience, messy, uneven, regional, but devastating enough in enough places that when later cultures went looking for a metaphor for overwhelming loss, the waters rose and covered the world was already waiting for them. And if that's what the late Ice Age could do given a few centuries of melt, imagine what happens when you take away the ice cap of an entire inland sea. 5. Zanclean Megaflood, refilling the Mediterranean 5.33 million years ago. Because if a few centuries of melting ice can redraw coastlines, what happens when you let an entire ocean fall off a cliff? To answer that, we have to jump way beyond human memory, way beyond human existence, into a world where our ancestors are still some distant, shrew-like primates in African forests. Roughly 6 million years ago, something strange started happening around the Mediterranean. Today we think of it as a classic inland sea, deep blue water ringed by Europe, Africa and the Middle East, connected to the Atlantic only by the narrow throat of the Strait of Gibraltar. But during a period known as the Messinian salinity crisis, it seems that connection partially, and maybe repeatedly, slammed shut. Tectonic plates are always grinding past each other. The African plate is slowly ramming into Europe. As the region buckled, the seafloor around Gibraltar may have heaved upward, building a natural dam between the Atlantic and the Mediterranean basin. Close that gate even a little, and the math gets ugly fast. The Mediterranean loses water constantly to evaporation. Modern estimates say over a metre a year, on average, if you didn't keep topping it up with inflow from the Atlantic and rivers. Cut off most or all of that ocean inflow, and the basin starts to behave less like a sea and more like a giant, leaky pan left on the hot stove. Over thousands of years, as river input and groundwater struggle to keep up with that evaporation, sea level inside the Mediterranean would start to fall. Not by a few metres, by hundreds, maybe more than 1,000. This is the nightmare scenario geologists are trying to reconstruct, a Mediterranean that didn't just shrink around the edges, but partially or largely dried down into a series of hypersalty lakes and deep desert-like depressions. Evidence for this comes from some very weird rocks. Across the Mediterranean seafloor, drill cores pull up thick layers of evaporites, minerals like gypsum and halite, rock salt, that form when huge volumes of seawater evaporate away, leaving behind their dissolved salts as crystalline leftovers. You don't get kilometre-thick stacks of evaporites from normal everyday evaporation. You get them from a basin that's been cut off, concentrated, and desiccated over and over again. Some of these salt deposits sit thousands of metres below modern sea level. That suggests the water column above them once dropped dramatically, exposing the basin to air, or at least turning it into a shallow hypersaline mess rather than a deep, open sea. Imagine standing where the central Mediterranean is now, but instead of waves, you're looking across a vast, shimmering salt flat, broken by scattered brine lakes and isolated pockets of deeper water. The surrounding coasts loom above you as cliffs, hundreds of metres high. Rivers like a proto-Nile plunge off those edges in spectacular waterfalls, racing down into the deep basin. If any large mammals had been living around the Mediterranean at that time, and they were, including early elephants and hippos, this would have been a tectonic Eden and hellscape combined. Newly exposed land bridges connecting Africa and Europe. Strange, enclosed valleys with exotic ecosystems. Blistering heat, salt storms and rivers carving canyon systems far below what's now the ocean surface. But the Messinian salinity crisis isn't our flood yet. It's the setup. The flood comes when that tectonic dam at Gibraltar fails. At some point around 5.33 million years ago, The connection between the Atlantic and the Mediterranean reopened. The key question is, how? One end of the spectrum is the gentle scenario. Maybe the dam subsided slowly, maybe sea level outside rose. Maybe erosion nibbled away at a narrow channel over tens of thousands of years, letting in a trickle that gradually grew. In this version, the Mediterranean refills like a giant bathtub with the faucet turned on low, taking a long, quiet time to reach modern levels. The other end is the megaflood. In that scenario, the difference in water level between the Atlantic and the desiccated Mediterranean basin wasn't a few meters. It could have been on the order of a kilometre. That's an enormous pile of potential energy parked right next to a half-empty hole. Once the Atlantic manages to punch even a small channel through whatever barrier sits at Gibraltar, a faulted ridge, a sill of uplifted rock, maybe partially blocked by sediments, water starts to pour in. As it pours, it erodes. As it erodes, the channel deepens and widens. As the channel deepens, the flow accelerates. Hydrologists call this positive feedback. To anyone watching from the shore, it would just look like the world breaking open. Computer models that plug in plausible numbers for water level difference, channel geometry and erosion rates suggest something wild. Under the right conditions, the Atlantic could have carved a deep gorge through Gibraltar and refilled most of the Mediterranean in as little as a few months to a couple of years. Not leisurely sea level rise, a wall of water potentially hundreds of meters high racing into the basin, scouring rock, dumping sediments, and driving a surge front that might have travelled hundreds of kilometers inland from the entry point before spreading and shallowing. The signatures of this kind of event are what geologists have been hunting. If there really was a Zanclean Megaflood, you'd expect to find a gigantic erosional channel cut into the bedrock sill at Gibraltar, like a fossil waterfall chute. You'd look for deep, steep-sided valleys on the Mediterranean side of the strait, carved by catastrophic flow. You'd comb seismic surveys of the seafloor for chaotic, thick deposits laid down quickly by monstrous currents, rather than the neat, layered sediments you'd expect from slow, steady refilling. And that's exactly where the argument begins, because what we see beneath the modern sea is dramatic enough that many researchers say this had to be catastrophic, while others insist you don't need a mega tsunami to get what we've got. To understand why they're fighting over that interpretation, we have to zoom in on those supposed scars of the flood and ask what exactly they're recording. Start with the most obvious suspect, the gateway itself. Beneath the modern Strait of Gibraltar, seismic surveys and drilling data reveal what looks suspiciously like an over-deepened trench cut into the bedrock sill. Instead of a smooth, gradual rise from the Atlantic into the Mediterranean, you see a kind of submerged canyon, several hundred meters deeper than you'd expect from normal erosion in such a narrow passage. Think of it as a ghost of a waterfall preserved in stone. On its Atlantic side, the margin drops off relatively gently. On the Mediterranean side, the profile steepens and plunges. That asymmetry is one of the first clues that got people talking about something more dramatic than a slow leak. In hydraulic terms, when water spills from a higher reservoir into a much lower one, most of the erosion happens downstream of the lip, where the jet of flow slams into the receiving basin and starts plucking rock loose. You'd expect the resulting channel to be deepest and steepest on the side facing the empty basin, gradually smoothing out as you move upstream toward the source. That's exactly the kind of geometry some teams argue we're seeing at Gibraltar, a knifed-down, over-incised channel that makes more sense if a torrent once roared through than if we just had a few million years of modest tidal exchange. But the channel at Gibraltar is only the beginning of the story. If a megaflood tore into a half-empty Mediterranean, that energy wouldn't stop at the sill. It would keep going, racing along the seabed of what was then a deep desert-like depression. As it did, it would behave a lot like a gravity current, a dense, fast-moving tongue of water hugging the bottom, accelerating down slopes and carving its way forward. So geologists have gone hunting for downstream scars. On the western Mediterranean seafloor, particularly in the Alboran Sea, and along the path you'd expect floodwater to take, they've mapped a network of giant erosional channels and scoured surfaces. Some of these features are tens of kilometres wide and hundreds of metres deep, with steep walls and flat floors that look more like subaerial canyons than gentle submarine valleys. The timing lines up suspiciously well. Many of these incisions appear to cut through older Messinian evaporites and are themselves overlain by younger Zanclean marine sediments, the very age of the proposed refilling. That stratigraphic sandwich is precisely what you'd predict if a catastrophic flow carved the basin after most of the salt had already been laid down, then was quickly drowned beneath rising post-flood seas. Further east, in the deeper parts of the basin, the story shifts from erosion to deposition. If you pour an ocean into a hole, all that water is going to carry an obscene amount of sediment with it, not just sand and mud, but boulders, chunks of the eroded sill, collapsed canyon walls, anything it can tear loose. As the current charges across the basin, it should dump that load in a very distinctive way. Thick, chaotic packages of material laid down rapidly, often with coarse stuff at the base and finer material above as the flow wanes. In the subsurface, those kinds of deposits show up as acoustic messes. When scientists run seismic sound waves into the seafloor, neatly layered muds and fine sediments return crisp, parallel reflections, tidy stripes that stack in predictable ways. Catastrophic deposits, in contrast, tend to look like jumbled, lens-shaped blobs, reflections cutting across each other, packages that thicken and thin abruptly, internal chaos sandwiched between more orderly layers. In several parts of the Mediterranean, especially in the deepest abyssal plains, researchers have identified exactly these kinds of chaotic units sitting right at the base of the Zanclean sequence. Beneath them, Messinian salts and older strata. Above them, the relatively calm, rhythmic drape of normal marine sedimentation over the last few million years. To megaflood proponents, this looks like a smoking gun. They argue that those basal Zanclean units represent colossal submarine fans and sheet deposits formed by incoming Atlantic waters as they plunged into the basin, spread out, and lost energy. In this view, each chaotic wedge is a frozen snapshot of the refilling surge, coarse at the bottom where the current first smashed in, finer upward as the deluge stabilized, and the Mediterranean transitioned back into a more ordinary sea. But not everyone buys that this chaos demands catastrophe. One of the central debates boils down to a simple question. How weird is weird when you're looking at sediments laid down over millions of years in a tectonically active basin? Normal ocean processes can do surprising things. Turbidity currents, underwater avalanches of sediment, can carve canyons and build huge submarine fans without any need for kilometre-high waterfalls. Slumping of unstable slopes can produce thick, jumbled deposits when layers of mud and sand collapse and slide down slope. Changes in sea level, shifts in sediment supply, and even earthquakes can all leave behind messy signatures in the stratigraphic record. Skeptics of the megaflood idea argue that many of the supposed flood scars could be explained by these more everyday processes, scaled up over time. An erosional channel at Gibraltar, perhaps a product of long-term tidal currents working on a structurally weak zone, modified by repeated phases of partial isolation and reconnection, over-deepened valleys and canyons on the basin floor. Maybe a legacy of sustained downslope flows from rivers and shelf edges during periods when sea level dropped and the margins were more exposed. Even those basal chaotic units under the Zanclean marine muds could in principle be the result of the Mediterranean switching abruptly from a salt-dominated restricted basin to a normal marine environment. The first rush of new ocean water might destabilize slopes, trigger mass wasting, and create a messy transitional package without requiring a single, unified megawave tearing across the entire sea in months. Where you land on this spectrum often comes down to how much weight you give to scale and timing. Supporters of a megaflood point out that the sheer volume and geometry of some of these erosional features and deposits are hard to reconcile with slow, intermittent processes. They emphasize the apparent synchronicity, channels and chaotic units of roughly the same age, spread across vast distances, all forming right at the moment the Mediterranean switched from Messinian to Zanclean conditions. Opponents counter that our resolution in deep time is limited. Right at the moment might still mean thousands of years in geological terms, plenty of time for multiple events, feedbacks, and gradual processes to stack up into something that looks sudden, when you're only sampling it every few tens of meters in a drill core. Underneath all of this is a deeper tension. Are we looking at the record of one unimaginably huge, short-lived event that refilled the basin in a geological blink? Or are we seeing the accumulated fingerprints of a complex, drawn-out transition where intermittent pulses of inflow, slope failures, and shifting gateways added up to a noisy but ultimately more gradual return of the sea? So far, the rocks offer hints in both directions. To push the argument further, we have to step away from the sediments themselves and ask a different kind of question. If a megaflood really did roar through Gibraltar and race across the desiccated Mediterranean, how fast could it have moved? How high might the water have risen? And what would a world living anywhere near that basin have actually experienced? To get at that, geologists and hydrologists have done something both very simple and very audacious. They've tried to turn the Mediterranean into a word problem. Take a basin that's on average several kilometres deep relative to the Atlantic. Drop sea level inside it by 1, 2, maybe 3 vertical kilometres. Put a narrow sill at the entrance, Gibraltar, that starts just a bit higher than the empty basin floor. Now open a crack in that sill. How fast does it fill? When you run that scenario through fluid dynamics, the answers stop feeling like a big flood and start feeling like cheating. In some models, once the connection at Gibraltar is fully breached, flow accelerates toward what's called critical or supercritical conditions, basically the hydraulic equivalent of breaking the sound barrier. Water jets over the sill and plunges into the abyss on the Mediterranean side, in a sustained wall of flow that makes Niagara look like someone left the tap on. You get discharges on the order of tens of millions of cubic meters per second. In more extreme setups, you flirt with 100 million cubic meters per second. For comparison, the Amazon, the largest river on Earth today, averages about 200,000 to 220,000 cubic meters per second. In other words, we're talking about something like 50 Amazons squeezed through a single gap, maybe more. Not for an instant, potentially for months. At those rates, the time it would take to refill a desiccated Mediterranean shrinks to mind-bendingly small numbers. Some calculations suggest the basin could have gone from mostly dry to mostly full in as little as a year or two. Others stretch it to a few hundred years if you assume a series of pulse-like flows, partial blockages, or a more complex gateway geometry. But even a few hundred years is a blink in geological terms. You can drain and refill small alpine lakes with landslide dams on that timescale. Doing it to an entire marginal ocean, that's a different category of violence. And this is where the Zanclean event, however exactly it played out, becomes important to more than just specialists arguing over Messinian salts. It's a proof of concept. It shows that given the right boundary conditions, an overdeepened basin, a perched water source, a narrow rock sill, Earth is fully capable of flipping a whole regional ocean between dry and full on timescales that, if you could watch them in real time, would look like catastrophe, not gradual change. Even at the conservative end of the models, you're still talking about coastlines migrating tens of kilometres inland within a human lifetime. Water levels rising metres per month, not millimetres per decade. That's not just sea level rise, that's the sea chasing you. Now, here's the catch, no human ever watched this happen. The Zanclean reflooding took place around 5.33 million years ago. The earliest things we'd comfortably call hominins, our broader lineage, were only just starting to appear in Africa. Think small-brained, chimp-sized apes still very much at home in the trees, with no boats, no language as we understand it, no myths. Modern humans, Homo sapiens, shows up maybe 300,000 years ago. Neanderthals and Denisovans a bit earlier. All of that is separated from the Zanclean flood by more than 5 million years of evolution. So why does this ancient event matter in a video about flood traditions? Because it blows up a lazy assumption many people carry around without realizing it, that when ancient cultures talk about the whole world flooding, they must be exaggerating because Earth simply doesn't do that kind of thing. It does, just not always on a schedule that lines up with our particular branch of the family tree. The Zanclean reflooding sits in the same category of phenomena as the breaking of superdams on Mars, or the drainage of enormous ice-dammed lakes during Earth's glacial periods. It's an example of what planetary scientists sometimes call catastrophic outburst floods, events where huge volumes of water stored behind a barrier are released in a single, sustained pulse. On Mars, those floods carved channels thousands of kilometres long and hundreds of metres deep in a geological instant. On Earth, during the last ice age, the collapse of glacial lakes like Missoula and Agassiz rearranged whole landscapes, dumped thick layers of sediment, and probably jacked sea level by noticeable amounts over just a few decades. The Zanclean event is all of that, scaled up one more notch. It involves not a lake, but a semi-enclosed ocean. Not a patch of continent, but an entire tectonic basin. Not a shoreline migrating across a valley, but coastlines rewriting themselves from Spain to Syria. When you see the world that way, not as a calm blue marble slowly weathering away, but as a machine that occasionally flips into rare high-energy modes, stories of the waters rising to cover everything stop sounding like naive poetry and start sounding like compressed memories of things the planet really can do. Even if the Zanclean Megaflood happened millions of years before anyone was around to name it, it expands the menu of possibilities. It tells you that ocean-scale floods aren't fantasy. They're part of Earth's repertoire, triggered when climate, tectonics, and sea level line up in the wrong or right way. And that has implications not just for how we read myths, but for how we think about risk. Because if the Mediterranean can, under the right circumstances, drain and refill like a bathtub, what about the other marginal seas? What about ice-covered basins during glacial maxima? What about the continental shelves that humans actually lived on during the last 100,000 years, now drowned but once dry plains where people built camps, hunted, told stories? If planet-scale hydraulics can flip that fast over a basin the size of the Mediterranean, then the kinds of floods our ancestors might have seen around the margins of shrinking ice sheets or rising seas suddenly look a lot less modest. But to connect those dots responsibly, we need to bridge a gap, from a flood no human witnessed to floods that people absolutely did, and then to the stories they told about them. That means stepping away from the Miocene and Pliocene, and back toward the world of our own genus, a world where ice sheets pulse, shelves drown, and whole coastlines vanish within the span of oral memory. But before we leave it behind, we need to be honest about something. Everything I've just described about the Zanclean reflooding, the roaring gateway at Gibraltar, the supercritical flow, the 50 Amazons through one notch, is a reconstruction. A very educated, very numerically modelled reconstruction. But still, a model. When scientists say Zanclean Megaflood, they're not pointing to a fossilized tsunami wave frozen in rock. They're pointing to a set of clues that can be read in more than one way. On one side, you have the people who look at those clues and say, this only makes sense if the Mediterranean refilled catastrophically. On the other side, you have just as qualified researchers saying, hang on. You can get a lot of this with something slower, maybe fast by geological standards, but not Niagara from orbit. So what are they actually arguing over? A few big things. First, the shape of the seafloor around Gibraltar and the western Mediterranean. If you run sonar over the strait and the adjoining basins, you see deep, over-excavated channels and scarps, features that look at first glance like the fingerprints of an enormous torrent. There's a giant groove carved into the Atlantic shelf leading toward the strait. There's a funnel-shaped depression on the Mediterranean side that could be the plunge pool where that hypothetical jet of water smashed into the basin floor. There are buried erosional surfaces and chaotic deposits right where you'd expect flood-out wash to land. Pro-megaflood folks point to these and say, come on, this is textbook catastrophic incision. You don't gouge bedrock like that with a gentle trickle over 1 million years. Skeptics counter, sure, they look dramatic, but remember how much time you've got to play with. 5-6 million years of changing currents, tides and sea levels can do weird things. You can get deep channels and erosional unconformities from persistent, strong flow without needing a one-and-done cataclysm. What would tip that scales decisively? Sharper, cleaner, more unambiguous geomorphology. If, for example, high-resolution imaging or drilling found a single continuous erosional surface that cuts across older deposits and then gets buried all at once under younger, uniform marine sediments, that would look very flood-like. It would say, something came through here in a short burst and reset the landscape in one shot. If, instead, the erosion and deposition turn out to be layered, stepped, and interrupted, several cut and fill cycles, different styles of sediment stacking, clear breaks in time, that leans more toward a complex multi-stage reconnection. Still fast in some moments, but not one apocalyptic surge. Second, the sediment itself, a flood that fills an ocean basin in, say a decade, should leave a particular kind of mess. You'd expect thick, coarse, badly sorted deposits right downstream of a gateway, boulders, gravels, sand all dumped together, tapering off into finer layers as you move east. You'd expect giant, cross-bedded structures formed by high-velocity flow, maybe even underwater dunes frozen mid-migration. You might even get mega ripples at scales we normally only see in the biggest river systems. Some cores and seismic profiles do show thick, chaotic packages in the right time window, around the boundary between the Messinian and Zanclean stages. That's a big part of what lit the megaflood fire in the first place. But the resolution is still fuzzy. A drill core only captures a narrow cylinder of mud and rock. Seismic surveys are like blurry X-rays. You can see that something happened quickly, but is it one insane season of discharge, or a few centuries of waxing and waning inflow? Future cores with precise dating and grain size analysis could help. If they reveal a razor-thin transition, Messinian evaporites on the bottom, a sharp erosional contact, then open marine Zanclean muds above, with no sign of intermittent drying or restricted circulation, that screams rapid reflood. If instead you find a gradational sequence, first some brackish or restricted marine deposits, maybe thin evaporites mixed with normal marine layers, then fully open ocean conditions. That's more consistent with a slower, stepwise filling where the basin sloshed and oscillated before locking into its modern state. Third, the fossils. Life is a surprisingly good stopwatch. When you refill a desiccated basin, you don't just pour in water. You pour in organisms, plankton, mollusks, fish, everything hitching a ride in the invading seawater. They show up in the sediment record as microfossils and shells. If those marine communities appear abruptly and synchronously across the whole Mediterranean, same open ocean plankton species, same general assemblages everywhere, all at essentially the same stratigraphic horizon that argues for a quick, basin-wide reconnection. One gateway opens, the whole thing floods, and biota from the Atlantic colonize it almost at once. If different sub-basins show staggered arrivals or prolonged intervals where local low-diversity communities persist before fully open ocean species dominate, that points to a more drawn-out story. Maybe some parts of the basin reconnected sooner, others stayed shallower or more isolated, and the final full ocean mode took longer to establish. Right now, the data is suggestive but not definitive. Some areas show very abrupt faunal turnovers, others look more transitional. People can, and do, interpret the same charts differently, depending on which mechanism they walked in preferring. Fourth, the timing of tectonics and climate. You don't get a dried-out Mediterranean for free. You need plate motions and global sea level changes to conspire in just the right way. Uplift at gateways like Gibraltar and the Sicilian Straits. A drop in global sea level, maybe changes in sediment supply that gradually choke off the connections. How quickly those processes reversed matters. If new seismic and structural studies were to show that the Gibraltar sill subsided in one relatively short tectonic pulse, a few tens of thousands of years, or even less, just as Atlantic sea level was high, that supports a scenario where the system flips from mostly sealed to wide open in one go. The flood models make more sense in that context, if instead the gateway seems to have deepened in several stages, with evidence that shallow, restricted passages existed for a long time before final deep opening, then a more incremental filling becomes easier to argue. You'd get strong, erosive flows during each deepening phase, but the basin wouldn't go from desert to deep sea on one dramatic Tuesday. So where does that leave us? Somewhere in the middle. The majority view right now is that the Mediterranean did refill relatively fast at the start of the Zanclean, fast enough that if there'd been humans watching, they would have used whatever words they had for "the world is ending." But the exact flavour of that speed is up for grabs. Was it really a single, sustained superflood blasting through Gibraltar, dropping shorelines by metres a week? Or a series of powerful floods and surges over a few centuries as the gateway progressively deepened and the basin sloshed toward equilibrium? The available evidence is consistent with something at least flood-like. It doesn't yet force us into the most extreme version of the story, and that's an important lesson for this whole video. Catastrophe and gradualism aren't binary switches. Earth often does both, layered together, long, slow build-ups of stress, sediment or ice, punctuated by brief, violent releases. The Zanclean reflooding sits right at that crossroads. The slow part, millions of years of plate motions, narrow straits silting up, global sea levels rising and falling, salt piling kilometres thick on a dying seafloor. The fast part, whatever actually happened when the Atlantic finally broke back in, whether it was a single megaflood or a rapid cascade of lesser ones. As new data comes in, sharper seafloor maps, better dated cores, more detailed fossil records, the balance may tip one way or the other. The megaflood might be confirmed in all its cinematic glory, or downgraded to just a brutally fast marine transgression. Either way, the big point stands. The Mediterranean didn't quietly, politely become what it is today. It snapped into that state through a transition so rapid that, scaled down to human time, it would have looked like a world-ending deluge. When we listen to flood myths from much later humans, people who actually did watch coastlines drown and rivers explode, that's worth keeping in mind. They weren't inventing the idea of apocalyptic water out of nowhere. They were living on a planet that, in deep time, had already proven it could empty and refill an ocean. So where does that leave all our flood stories? We've just walked through 5 very different kinds of deluge. A quiet inland sea turned into a roaring waterfall at the Bosporus, maybe drowning Neolithic villages around the Black Sea coast fast enough that the sea rose wasn't a metaphor. It was Tuesday. An entire shelf edge collapsed off Norway and sent a wall of water ripping across the North Atlantic, erasing coastlines and turning places like Doggerland from hunting grounds into coffin lids. A glacial dam in Montana failed not once, but over and over, unleashing inland seas that blasted the Pacific Northwest into the Channeled Scablands, carving features so absurd that geologists spent decades refusing to believe they could be real. An Ice Age pulse raised global sea level by tens of meters in what, to human eyes, would have looked like an endlessly repeating nightmare. Every generation watching the shoreline step back, fields vanish, marshes expand, rivers back up, with no idea where it would stop. And then, underneath all of that, the deep time prequel, an entire inland ocean shut off from the world, evaporated to salt and brine, then refilled in a geologic eye blink by the Atlantic breaking through at Gibraltar. A flood on a scale that makes every later story feel like a puddle. The details are different coastlines, different mechanisms, different victims, but the pattern is the same. Water held back or held up by ice, by rock, by tectonics, by narrow straits, slowly accumulating potential. Then one day, the barrier fails. From the point of view of a planet, that failure is fast. From the point of view of a person standing on a beach watching the tide do something it has never done before, it's instantaneous. This is why the idea of a great flood is so sticky. It's not just a story someone made up because water is spooky. It's something our species has lived through again and again, in different places and on different scales. Not one single global bathtub to the brim flood that politely covers the Himalayas and then drains away. Instead, layers. A shelf-edge tsunami here, a collapsing ice dam there, a coast that drowns over a few generations, a plain that disappears overnight, an inland sea that turns into an ocean, an entire basin that goes from salt pan to deep blue in what, in geologic terms, is the time between breakfast and lunch. When people later tried to explain what their grandparents or their gods had survived, they reached for the biggest tool their language had: the world. Not my village, not our valley, but everything. If your entire known universe is the basin of the Tigris and Euphrates, and one spring the rivers don't just flood, they don't stop, they climb, they eat the horizon, then yes, the whole world was underwater. You don't need satellites to feel like creation is being unmade. That's the thread tying global myths to the science. Not a one-to-one map. This verse is that flood. This hero is that refugee, but a shared physics of catastrophe. You hold a system near some critical threshold, an ice sheet near its buoyant limit, a sea behind a narrow sill, a slope overloaded with sediment, and it looks boring. Stable, eternal. Then it crosses the line and behaves in a way that feels to anything small enough to tell stories, like a miracle or a curse. What science has done over the last century is peel back the quiet parts, the slow loading, the invisible strain. It shows us that behind the myths of sudden judgment and instant transformation, there really are moments when water stops behaving like scenery and starts acting like an animal. So when you hear about a god deciding to wash the slate clean, or a culture remembering that once long ago the sea came in and took everything, the choice isn't between pure fiction and literal footage of a single event. There's a third option. They were remembering, in distorted poetic form, the way this planet actually works. And it cuts both ways. On one side, it makes the myths more interesting. You don't have to flatten them into cartoon physics or defend them as eyewitness reports of something that clearly didn't happen exactly as written. You can see them as human attempts to make sense of living on a world that snaps, jerks, and lurches as often as it drifts. On the other side, it makes the science harder to ignore. Because we are, right now, quietly loading another system. Coastlines lined with cities instead of mammoths, ice sheets melting from the edges in, rivers trapped behind concrete instead of moraine. We know sea level is rising again. Not at Zanclean speeds, not yet, but fast enough that stretched over a lifetime, it will look more like a story than a statistic. In a few thousand years, if anyone's still telling tales, they might remember this as the age when the waters returned. And those people will be just as tempted as our ancestors were to say, the whole world flooded. Even if, geophysically, it was just a series of regional catastrophes layered over a global transgression. That's the deeper point of looking at flood layers instead of hunting for one single magic deluge. It shifts the question from, did the flood happen? To, how often does the earth do something that would feel, to us, like the flood? The answer is, more often than we'd like, on human timescales. These are once-in-a-civilization shocks. On planetary timescales, they are just one of the ways energy gets redistributed when it can't stay where it is anymore. Our ancestors survived them by moving, remembering, and telling stories. We have better tools, tide gauges, satellites, models, but we're still doing the same thing. Trying to see it coming, trying to explain it to children, trying not to look directly at the part where the maps change. So, here's what I want to know from you. Where are you listening from? Which coastline? Which river valley? Which high plateau? Are you sitting on land that used to be seafloor, or looking out at an ocean that used to be a forest? Drop it in the comments. Tell me what the world flood would actually look like where you are. Would it be the river jumping its banks, the tide swallowing the boardwalk, the lake climbing past the last cabin, or the storm drains burping seawater up into the middle of town? If you learned something in this episode, or if it gave you a new way to think about the stories you grew up with, hit like so more people actually see it. If you've got your own favourite flood candidate we didn't talk about, an ancient lake outburst in your region, a myth you think lines up with some specific event, or even a wild hypothesis you want to see tested, throw that in the comments too. I read as many as I can, and it helps shape what we dig into next. And if you want more deep dives like this, where we take big mythic ideas and see what the rocks, the genomes and the models have to say about them, make sure you subscribe. That's the easiest way to stay in the loop as we tackle other impossible stories. Fire from the sky, winters that lasted years, animals that sound like dragons because they kind of were. If you really want to support the show, though, the best place to do it is by listening on Spotify. There's a link in the description. Streaming the episodes there helps more than anything else to keep this going. And it signals to the algorithm gods that people actually care about long, weird, evidence-based storytelling. In the end, whether you come at this as a believer in ancient texts, a fan of hard geology, or just someone who likes big, unsettling ideas, we're all in the same position as those Neolithic farmers on a rising shore. We live on a restless planet. It fills and empties seas. It lifts and drops continents. It builds ice like cities, then melts it like wax. Every once in a while it lets water show us just how small our sense of forever really is. Our job isn't to pick one story and cling to it, it's to hold both. The myth that says, once, the waters came and remade the world, and the science that says, yes. And here are 5 times we can prove it did something very much like that. Thanks for listening. Stay curious, stay kind to the people stuck on low ground, and I'll see you in the next one.